Right now, even if you are lying perfectly still, Earth is carrying you eastward at a speed that may exceed 1,500 kilometers per hour. And yet your body feels no shaking. The air does not rush past in a violent storm, and everything around you remains exactly where it is. How can a motion this immense be almost impossible to feel? Welcome to Night Cosmos Sleep. In today's story, we will explore why Earth is constantly rotating while the ground beneath us seems completely still. The answer is not that our planet is moving too slowly, but rather in the way the human body senses motion, and in the fact that everything around us shares that same movement. At the equator, Earth's surface travels at roughly 1,675 kilometers per hour, covering nearly 40,000 kilometers in a single rotation. Across most of Vietnam, that speed still exceeds 1,500 kilometers per hour. Yet our homes, roads, cities, and bodies are all being carried along together, leaving no nearby stationary point against which we can compare our motion. The human body does not directly sense constant speed. Instead, it mainly detects changes in speed. When a car accelerates, brakes suddenly, or changes direction, we feel our bodies pulled or tilted, but once the vehicle settles into steady motion, that sensation fades considerably. Earth also rotates with remarkable consistency. It does not suddenly speed up each morning and come to a stop at night. The atmosphere is not standing still in space while Earth spins beneath it. The air, the ground, the oceans, and every person on the planet already share Earth's rotational motion. Gravity keeps everything drawn toward the center of the planet, while inertia allows our bodies to continue moving with the surface instead of being left behind. Although we cannot feel Earth turning, we can still see the traces of its motion. The sun appears to rise in the east and set in the west. The stars slowly drift across the sky, and shadows change position throughout the day. These familiar sights are where we begin to understand that it is not the entire sky moving above us, but the planet beneath our feet. Each morning, the sun seems to begin its journey in the east, but the true motion is taking place below us, as Earth quietly turns toward the light. There is something rather strange about every morning. The sun does not truly rise in the way our eyes perceive it. It does not begin an orbit around Earth, nor does it slowly climb from beneath the horizon into the sky. The most obvious motion before us is largely created by another movement that our bodies do not sense at all. Imagine a beam of sunlight passing through a window. At first, it rests near the edge of the floor. A little while later, the patch of light has shifted to one side, and the shadow of the window frame has changed position as well. If you mark the tip of a post's shadow in the morning and return an hour later, the new mark will be noticeably separated from the first. The post has not moved, and the ground has not turned relative to the house. Yet the direction of the light has changed. From the ground, the answer seems almost too obvious. The sun is traveling across the sky. It appears in the east, rises higher around midday, and then descends toward the west. At night, the moon and the stars seem to do the same, while trees, mountains, and houses appear to remain perfectly still. This everyday experience led people throughout most of history to believe that the heavens revolved around an unmoving Earth. It was not a foolish idea. Relying only on sight and bodily sensation, nearly all the evidence seemed to support it. We can see the sun moving, but we cannot see the ground turning. We feel the floor beneath us standing still, but we do not feel the speed being carried by the entire room. Human vision, however, only tells us that the position of an object has changed relative to the observer. It does not always tell us which side is actually moving. While sitting on a smoothly moving train, a passenger may see trees and utility poles rushing backward. If another train beside it begins moving slowly, the passenger may sometimes feel as though their own car is sliding away, even when it remains stationary. The brain must rely on the surrounding scenery to decide what is moving, and for a few seconds, it can reach the wrong conclusion. The sky creates a similar impression each day, only on a vastly greater scale. The sun appears to travel from east to west, while the observer and the ground beneath them are actually rotating in the opposite direction. Earth turns from west to east, carrying the continents, oceans, atmosphere, and everyone on its surface along with it. Because we are being carried eastward, the sky appears to drift westward. Dawn, Ben, is not the moment when the sun begins moving around us. It is the moment when Earth gradually rotates our location into the illuminated region. First, sunlight reaches the upper atmosphere above the horizon, causing the sky to brighten. Then the edge of the sun appears as the planet's surface continues turning toward the source of light. Earth does not stop during the hours that follow. The observer's position continues changing relative to the sun, making it appear to rise higher in the sky. Near midday, sunlight strikes the ground at a steeper angle, so the shadows of trees and buildings usually grow shorter. By afternoon, Earth's rotation carries that location toward the opposite edge of the illuminated region, making the sun appear to sink lower in the west. Sunset is also simply a change in perspective. The sun does not switch off or vanish from space. The horizon hides it because the place where we are standing is turning toward Earth's unlit side. At the same moment, noon may not yet be over in another region farther west, while even farther away, another city may just be greeting the dawn. Viewed from space, day and night do not take turns covering the entire planet. They exist simultaneously on opposite sides. One half faces the sun and is illuminated, while the other lies in darkness. As Earth rotates, each city, field, and ocean passes through the boundary between those two regions. That boundary is constantly moving across the planet's surface. It may be bringing morning to one place while carrying sunset into another. Seen this way, day and night are not things the sun brings and then takes away. They are regions we pass through one after another as Earth turns. This movement is much faster than it appears. Across the sky, the sun and stars have an average apparent motion of about 15 degrees per hour. If a full circle of 360 degrees is divided into 24 parts, the sky seems to pass through roughly one such section every hour. 15 degrees may still be difficult to picture, but there is a simpler way to understand it. The sun's apparent diameter in the sky is only about half a degree. With an apparent motion of nearly 15 degrees per hour, the sky shifts by a distance equal to the visible width of the solar disk in about 2 minutes. This means that while someone prepares a cup of tea, the sun has moved across the sky by nearly its own visible width. The motion is too slow to create the sensation of rushing, yet fast enough to make shadows change position continuously. We do not notice it from second to second. But when 2 moments separated by only a few minutes are compared, the evidence already begins to appear. This is also the simple principle behind a sundial. A vertical object casts a shadow, and the sun's apparent motion causes that shadow to change direction over time. Long before mechanical clocks and digital displays existed, people could track part of the planet's movement using nothing more than a post and a marked surface. What is interesting is that the shadow does not directly reveal whether the sun is moving or Earth is rotating. It records only the changing angle between the light and the surface. To understand the true cause, people had to reverse their familiar point of view. Instead of imagining the sun racing around them, they had to imagine the entire ground turning beneath a distant source of light. A time-lapse camera can make this reversal much easier to see. When several hours are compressed into a few seconds, the shadows of buildings sweep across the ground, beams of sunlight travel through a room, and the sun traces a broad arc through the sky. A world that once appeared motionless begins to reveal its movement. Yet it is not only the shadows or the scenery in the footage that are moving. The camera, the room, and even the viewer are all being carried along by Earth. At night, the sky continues to leave behind evidence. If a camera is fixed in place and its shutter remains open for several hours, the stars stretch into glowing arcs. Those trails may appear to show the heavens rotating around Earth, but in reality, the tripod has been turning with the planet's surface while pointing toward the distant depths of space. Even so, if we look only at the room around us, this motion is almost impossible to detect. The table, the walls, the air, and our bodies are all moving together. Nothing passes by to provide a fixed reference point. Just as inside a train that has reached a steady speed, everything near the observer shares the same motion. The sky becomes a useful frame of reference because the sun and stars are so far away. As Earth changes its orientation, their apparent positions shift across our field of view. In other words, we do not directly see the planet turning. We see its rotation reflected in objects that are not being carried around with us in the same way. After nearly 24 hours, the sun returns to almost the same position in the sky. Light appears again in the east, the shadow of the window frame passes through familiar places, and a new day begins. This steady repetition became the foundation of clocks, daily routines, and the human sleep-wake cycle. The word almost, however, is important. While Earth is rotating on its axis, it is also moving farther along its orbit around the Sunday. So, after completing one rotation relative to the distant stars, Earth must turn through a small additional angle for the Sun to return to nearly the same position as before. The difference amounts to only a few minutes, and we will explore it more closely when we examine the planet's natural clock. The position of sunrise also changes with the seasons. At certain times of year, the sun appears farther north along the horizon, while several months later it rises farther south. This happens because Earth's axis is tilted and the planet is moving around the Sunday. Yet even as the point of sunrise shifts, the direction of the daily motion remains the same. The sky appears to move from east to west because Earth rotates from west to east. An ordinary morning therefore contains far more information than it seems. Shadows reveal that the angle of sunlight is changing. The sun's position shows that the observer is being carried into a new orientation. The arrival of day and night reveals that each region of the planet is turning into the light and then away from it. What is remarkable is not that these clues are too small. They are everywhere, from the shadow of a simple post to a band of sunlight crossing the floor. What is remarkable is that we have lived inside this motion since the moment we were born, while nearly everything around us has been moving with us. With no stationary background close at hand, the ground continues to feel completely still. Morning is not the moment when the sun begins its journey around Earth. It is the moment when the motion of the planet itself becomes visible through light. The sun rises, the shadows of trees grow shorter, and the afternoon drifts towards sunset because the place where we stand is continually changing direction in space. But once we understand that we are the ones being carried along, another question immediately appears. During the 2 minutes it takes for the sun to shift by roughly its own visible width, how far has the surface of Earth beneath our feet traveled? And over the course of an entire day, just how fast is the planet carrying us? During the time it takes you to listen to a 4-minute song, Earth may have carried your home more than 100 kilometers around the planet's axis. No road rushes past the window. There is no sensation of being pressed into the back of a chair. And when the song ends, every object remains exactly where it was. The number may sound impossible, but it comes from a very simple fact. Earth takes nearly 1 day to carry every point on its surface through a complete rotation. To grasp the scale of this motion, imagine the planet as an enormous sphere turning around a line that passes through both poles. This imaginary line is Earth's axis of rotation. Every place on the surface moves around that axis, but not every location travels the same distance. A person standing at the equator lies on the widest circle around the planet. During each rotation, that person must travel around Earth's entire waist. The circumference there is about 40,000 kilometers, nearly the distance of a journey around the world. Because the rotation is completed in close to 24 hours, the speed at the equator reaches roughly 1,675 kilometers per hour. Another way to picture it is that the equatorial surface moves more than 460 meters every second. In the time it takes someone to blink, the ground has already traveled a considerable distance around the planet's axis. This speed is even greater than the speed of sound in air under ordinary conditions, yet no sonic boom appears. The reason is that the ground is not racing through a stationary atmosphere. The air near the surface is also being carried along in the same shared motion. However, 1,675 kilometers per hour is not the speed of every place on Earth. As you move away from the equator toward the north or south, the circle a location must travel through each day becomes smaller. The time required to complete one rotation remains nearly the same, but the distance is shorter, so the speed measured in kilometers per hour decreases. You can picture this with a spinning disk. A point near the outer edge must travel around a large circle, while another point close to the center moves through a much smaller one. Both complete a full rotation in the same amount of time, but the point near the edge must move much faster to keep pace with the shared rotation. Earth works according to the same principle. Every location turns through 360 degrees in nearly 1 day. In other words, they all share the same angular speed. But the number of kilometers traveled depends on how far that location lies from the axis of rotation. The equator is farthest from the axis, while the two poles are located where the axis passes directly through the surface. This creates an interesting paradox. A person at the equator and another near the North Pole may both wait for the sun to return to nearly the same position in the sky. Each experiences one day, yet the distances Earth carries them around its axis are entirely different. The person at the equator has traveled nearly 40,000 kilometers, while the person near the pole has moved around a much smaller circle. At the North or South Pole itself, that circle shrinks almost to a single point. Someone standing exactly at a pole is no longer being carried along a path thousands of kilometers wide. They are almost simply turning in place around the planet's axis, like someone standing at the exact center of a spinning disk. After one day, that person has still completed a full rotation in angular terms, but has traveled almost nowhere horizontally around the axis. Vietnam lies north of the equator, so the surface speed there is lower than the maximum of 1,675 kilometers per hour. But the reduction is not large enough to make the motion slow. In southern Vietnam, Earth's surface is still carrying everyone eastward at about 1,640 kilometers per hour. In the north, the speed is around 1,560 kilometers per hour. This difference does not mean that southern Vietnam completes a day faster than northern Vietnam. Both regions still make one full rotation in nearly the same amount of time. The south lies closer to the equator and therefore travels along a wider circle. The north is slightly closer to the axis of rotation, so the distance covered during each turn is smaller. Imagine two houses, one in southern Vietnam and the other in the north. Over the course of 1 hour, the southern house is carried about 80 kilometers farther around the axis than the northern one, yet the people inside either house feel no difference. Their clocks move at the same pace, objects remain still, and the sun continues across the sky in its familiar cycle. In southern Vietnam, a house may travel more than 27 kilometers around the axis in just 1 minute. In the north, the distance is still around 26 kilometers. A car would need several minutes to cover that much ground. Yet the house does so without leaving its foundation in any way that the people inside can detect. After an hour, the distance is greater than the separation between many cities. After a day, the house may have been carried tens of thousands of kilometers around Earth's axis. And yet, the next morning, it still stands on the same street, beside the same houses, and beneath the same row of trees. This does not mean the house has gone on a journey and returned while the city remained behind waiting for it. The entire street, city, country, and surrounding ocean have all been carried along together. The distances between them remain nearly unchanged. So, from within the system, everything continues to appear motionless. This is where the idea of speed can become misleading. An object may be moving extremely fast relative to a distant reference point while remaining completely still relative to other objects traveling with it. A passenger on an airplane does not race toward the back of the cabin at hundreds of kilometers per hour because the seat, the floor, and the air inside the cabin all share the passenger's velocity. In the same way, a person standing in Vietnam is moving rapidly around Earth's axis when measured relative to the axis itself or from a viewpoint in space. But relative to the floor, the table, or someone standing nearby, that speed is almost zero. Every reference point the body uses in everyday life is taking part in the same journey. Viewed from above the North Pole, Earth would appear like an enormous disk turning counterclockwise. Cities near the equator would trace broad circles, while places at higher latitudes would follow smaller ones. Each path would close after nearly 1 day, but their lengths would be noticeably different. From space, this motion would not be invisible at all. The continents would continually change their orientation. One region would move into daylight, while another slipped away from it. Cities near the equator would sweep through space the fastest, while areas near the poles would rotate more slowly around small circles close to the axis. For someone standing on the surface, however, no landscape rushes past to reveal that speed. The horizon, the mountains, and the air near the ground are all moving in the same direction. As a result, a speed greater than 1,560 500 kilometers per hour exists without creating the sensation of sitting inside a rapidly moving vehicle. There is another important distinction to make. Rotation around Earth's axis is not the only motion we carry with us. Earth also travels around the Sun at a far greater speed, while the solar system itself moves through the Milky Way. Yet in this chapter, rotation alone is enough to raise a difficult question. How can the body ignore a speed this immense? Part of the answer is that speed by itself does not create a sensation. On a straight, smooth road, a car may travel quickly, while its passengers notice only by looking at the scenery outside. The strongest sensations usually appear when the car accelerates, brakes, or changes direction. The body is more sensitive to changes in motion than to a velocity maintained at a steady rate. Earth does not accelerate from rest to more than 1,500 kilometers per hour at sunrise. Nor does it slow to a stop when the sun sets. The planet was already turning before any of us were born, and from the moment our bodies began to form, they shared that motion. There was no sudden beginning that pressed our backs into a seat or violently disturbed the fluid inside the inner ear. Even so, motion across Earth's surface is not perfectly straight. Every location follows a circular path, which means its direction is constantly changing. In physics, a change in direction is also a form of acceleration. So why do our bodies still fail to notice that they are carried along a curved path? The answer is connected to Earth's enormous size. The circle we travel around is so wide, and one rotation takes so long, that the change in direction during any single second is extremely small. The surface may be moving at more than 1,500 kilometers per hour, but the planet's curve extends across thousands of kilometers. The body is not forced into a sudden turn as it would be when a car enters a sharp bend. Consider two different kinds of rotation. On a fast spinning amusement park ride, the passenger may sit only a few meters from the center while completing a full circle in several seconds. The direction of motion changes rapidly, so the body feels a strong outward pull. On Earth, the distance to the axis may be thousands of kilometers, and one rotation lasts nearly an entire day. The change in direction happens so gently that its effect is far smaller than the force of gravity holding the body to the ground. Speed, then, is only one part of the story. Learning that a house in Vietnam may be carried more than 1,500 kilometers in a single hour is certainly surprising, but it does not yet explain the quiet sensation inside that house. To understand this, we must look at how the senses detect motion. The inner ear is not an instrument that measures absolute velocity. The muscles do not know how fast the body is traveling relative to a distant point in space. The brain must rely on acceleration, changes in posture, and the relative motion of the surrounding scenery. When all these signals remain nearly constant, even immense speed can become completely silent. During the past hour, the ground beneath you may have carried you farther than a short flight. Yet no airport has appeared, no luggage has been required, and you are still sitting in the same room. The journey is invisible because the entire familiar world around you is traveling with you. Earth's rotational speed is clearly not small. So why does the inner ear sound no alarm? Why do the muscles not have to work constantly to maintain balance? And why does the brain continue to insist that the body is standing still? To answer that question, we must understand one very important limitation of the senses. The body does not truly measure speed. It mainly measures what happens when speed changes. In a balance test used in aviation research and training, participants are seated in a rotating chair. When the chair begins to move, they can clearly feel themselves spinning. But if it continues rotating steadily at the same speed, that sensation gradually fades. After a while, a person who is still turning may feel as though they have almost come to a stop. Something even stranger happens when the chair stops. The room is no longer rotating, and the body is no longer moving, yet the person may feel as though they are spinning in the opposite direction. This experiment reveals an important limitation of the senses. The inner ear responds strongly when motion begins, changes, or ends, but it does not always continue to report accurately once that motion becomes steady. During rotation at a constant speed, nerve signals from the semicircular canals gradually return close to their resting level. This is the key to understanding why we do not feel Earth turning. The human body does not contain an internal speedometer that reports how many kilometers per hour it is traveling. Our senses mainly detect changes in motion, when the body speeds up, slows down, tilts, or changes direction. When a car begins to accelerate, the passenger's back is pressed into the seat. If the car brakes suddenly, the body moves forward. When it turns quickly, the passenger leans to one side. These sensations do not arise simply because the vehicle is traveling fast. They appear because its speed or direction has just changed. Once the car moves steadily along a straight road, the sensation of being pushed quickly disappears. The people inside can read, talk, or sleep. The vehicle is still moving, but the body is no longer receiving a change strong enough to keep sounding an alarm. An airplane offers an even clearer example. During takeoff, passengers feel themselves pressed into their seats because the aircraft is rapidly gaining speed. But once it reaches cruising altitude and settles into steady flight, people can stand, walk along the aisle, or place a cup of water on a tray table. The airplane may still be traveling at nearly 900 kilometers per hour, yet inside the cabin, that motion almost disappears from awareness. If the window shades are closed and the engine noise remains constant, the body has great difficulty distinguishing between an airplane at rest and one moving steadily through the sky. The seats, the cabin floor, the air, and the passengers all share the same velocity. There is no nearby stationary object passing by for the eyes to use as a point of comparison. Earth places us in a similar situation. The floor, the trees, the cities, the oceans, and most of the atmosphere all share the planet's rotation. A person may be carried eastward at more than 1,500 kilometers per hour. Yet relative to the table beside them, their velocity remains almost zero. To understand how the body detects motion, we must look at a small system located deep within each ear. 3 semicircular canals are arranged in different orientations and filled with fluid. When the head begins to turn, the fluid temporarily moves differently from the walls of the canals, bending sensory cells and sending signals to the brain. The semicircular canals mainly help detect rotational movement and changes in direction. 2 other structures in the inner ear, often referred to together as the otolith organs, help sense linear acceleration and the direction of gravity. The brain combines these signals with information from the eyes, muscles, and joints to determine whether the body is tilted, upright, or moving. This system works continuously, though we rarely notice it. When the head turns to one side, the eyes automatically move in the opposite direction to keep the image relatively stable on the retina. Because of this reflex, the world does not dissolve into a blur whenever we walk or turn our heads. Signals from the inner ear not only create our sense of balance, but also help control eye movements and posture. The inner ear, however, is not a perfect instrument. It can be deceived when motion continues for a long time, or when visual information conflicts with signals from the balance organs. This is not merely a laboratory phenomenon. In aviation, it can become a genuine danger. When an airplane enters a very gradual bank, the motion may not be sudden enough for the inner ear to detect clearly. After the aircraft has been turning at an almost constant rate for some time, the pilot may feel as though it is flying straight. If the pilot then returns the airplane to level flight, the inner ear may create the sensation that the aircraft is banking in the opposite direction. The United States Federal Aviation Administration calls one form of this illusion the leans. In more serious situations, a pilot caught in a spin may lose the sensation of rotating. When the aircraft exits the spin, the body may create the illusion of turning in the opposite direction, causing the pilot to feel an urge to return the airplane to its previous and dangerous position. For this reason, when flying through clouds or darkness, pilots must trust their instruments rather than relying only on bodily sensation. These illusions may sound frightening, but they reveal a very useful principle. The body detects changes in motion more easily than motion that has been maintained steadily. A distinct turn produces a strong signal. A constant rotation that continues for long enough may gradually fade from awareness. Motion sickness also arises from the interaction of several senses. When someone reads a book inside a car, the eyes see a page that appears almost motionless, while the inner ear continues to detect the vehicle accelerating, braking, and turning. The brain receives two stories that do not completely agree. This conflict can lead to dizziness, nausea, and disorientation. NASA is especially interested in this problem because astronauts must move between environments with very different gravitational conditions. On Earth, the inner ear is accustomed to gravity, always providing a clear sense of downward direction. When a spacecraft enters orbit, astronauts experience microgravity, and that familiar signal changes suddenly. An astronaut's eyes can still see the ceiling, floor, and walls of the cabin, but the inner ear no longer receives the same gravitational cues it experienced on the ground. The brain must learn to interpret these signals in a new way, and during the early stages, some astronauts may experience space motion sickness, disorientation, changes in coordination between the head and eyes, or difficulty controlling posture. According to NASA, adapting to the new gravitational environment can take several days. This shows that the body responds strongly when the conditions of motion or gravity change. Astronauts do not become sick simply because their spacecraft is traveling rapidly around Earth. Orbital velocity itself is not the direct cause. The problem appears when the balance system encounters a new set of signals unlike those the brain learned to interpret on the ground. Earth does not expose our bodies to such a sudden change. The planet does not remain still at night and then accelerate in the morning. Nor does it slow down when the sun sets. Its rotation has continued for an immense span of time, beginning long before human beings appeared. Each person begins developing inside a body that already carries Earth's rotational velocity. After birth, we continue moving with the ground, the air, and everything around us. There is never a moment when the body must go from rest to more than 1,500 kilometers per hour in just a few seconds. Because there is no sudden start, the inner ear receives no signal like the one produced when an airplane takes off. But Earth does not carry us along a straight path. Every location on the surface travels in a circle around the planet's axis. Even when the magnitude of velocity remains nearly constant, its direction is continuously changing. In physics, a change in direction is also a form of acceleration. So why does this acceleration not make us feel as though we are sitting on a spinning ride? The difference lies in scale. An amusement park ride may complete a full rotation in only a few seconds, with a radius of just a few meters. The rider's direction of motion changes very quickly, causing the body to feel a strong pull. Earth takes nearly an entire day to complete one rotation, while its radius extends for thousands of kilometers. The curve our bodies follow is so broad that the change in direction during each second is extremely small. At the equator, the acceleration associated with Earth's rotation is about 0.034 meters per second squared. Compared with gravitational acceleration, which is approximately 9.8 meters per second squared, this amounts to only about 0.35%. In other words, the effect of Earth's rotation is hundreds of times weaker than gravity. That figure of 0.35% does not mean rotation has no effect at all. A person at the equator does have a slightly lower effective weight than they would if Earth were not rotating. But the difference is far too small for the body to notice in ordinary life. The curvature of the path also changes too gradually to strongly disturb the fluid inside the inner ear. Over the course of 1 second, Earth turns through only an extremely small angle. There is no sudden tilt, no noticeable increase in speed, and no new signal strong enough to trigger an alarm in the balance system. Another part of the answer lies in vision. The brain often recognizes motion by watching the surrounding scenery move past. From a car, trees and utility poles appear to rush backward. Inside an elevator, floors disappear past the opening of the doors. But on Earth, everything close to the observer is rotating along with them. The table does not move across the room. The mountain does not slide along the horizon. The air near the surface does not race westward at more than 1,000 kilometers per hour. Without a nearby stationary background, the eyes do not receive enough information to report that the body is being carried around the planet's axis. Only extremely distant objects reveal this motion. The sun moves across the sky, and the stars form glowing arcs in long exposure photographs. But these changes unfold over many minutes or hours, far more slowly than the kinds of motion the nervous system normally needs to respond to in order to maintain balance. In a sense, the brain gives priority to information that is useful for immediate survival. A floor that suddenly tilts, a car that brakes sharply, or an object rushing toward us all require an instant response. A rotation lasting nearly 24 hours and shared by the entire surrounding environment does not create the same urgency. The body therefore concludes that we are standing still. That conclusion is correct relative to the room, the street, and the ground directly beneath our feet. It becomes incorrect only when we compare ourselves with Earth's axis, the sun, or the distant stars. This also shows that there is no single velocity the body can call absolute. A person may be motionless relative to a chair while moving around Earth's axis. Earth, in turn, moves around the sun, while the sun travels through the Milky Way. The sensation of standing still always depends on the reference point used for comparison. The body does not ignore Earth's motion simply because it has grown accustomed to it. The deeper reason is that our sensory organs are designed to detect acceleration, changes in posture, and disagreements between different signals. Earth's rotation is remarkably steady. Its acceleration is extremely small compared with gravity, and the entire environment around us shares the same motion. The rotating chair experiment shows that the sensation of movement can disappear even while the motion continues. The illusions experienced by pilots reveal that the inner ear may fail to detect steady rotation. Research involving astronauts, meanwhile, demonstrates that the body responds clearly when the gravitational environment truly changes. Earth produces no such dramatic changes during an ordinary day. The inner ear sounds no alarm, the eyes see no scenery rushing past, and the muscles have no need to make an emergency adjustment. An immense motion becomes silent because it remains steady and is shared by nearly everything around us. But this only explains why we do not become dizzy or feel ourselves being sharply pulled. Another question remains. If Earth is a rotating sphere, what keeps people, the oceans, and the atmosphere from being thrown away from its surface? The answer lies in a force far stronger than the effects of rotation, a force that makes down at every location on the planet point toward the same place. That force is gravity. Right now, somewhere near the opposite side of Earth, a person may be standing with their feet pointing almost directly toward yours through the center of the planet. On a globe positioned with the North Pole at the top, that person appears to be standing upside down, as though they might fall from the underside of the world the moment they let go. From their perspective, we are the ones hanging upside down. So who is standing the right way up? The answer is both of us, because space has no single downward direction shared by the entire universe. There is no bottom beneath the planets toward which everything must fall. On Earth's surface, down is defined by gravity and almost always points toward the center of the planet. A person in the northern hemisphere drops a key from their hand. Someone in the southern hemisphere does the same. Viewed from far away, the two keys may fall in nearly opposite directions, but both are moving inward toward Earth. To each person, the motion is simply a fall toward the ground. This is difficult to notice in everyday life because we observe only a tiny portion of the planet. The floor appears flat, walls stand upright, and objects dropped near one another seem to fall along parallel paths. If those paths were extended through the entire Earth, they would gradually angle toward one another and converge near the central region. Gravity can be imagined as countless invisible threads connecting everything to the interior of the planet. One thread holds the listener's body. Others hold the trees, mountains, oceans, and every layer of the atmosphere. They do not all pull toward a single direction outside Earth. Instead, they point inward from every location on the surface. Gravity does not actually work through invisible strings. Every part of Earth's matter contributes to its gravitational pull. Rock near the surface, material deep within the mantle, and the core below all combine to draw objects inward. Because the planet is nearly spherical, that pull points approximately toward its center. Standing upright, therefore, does not mean that everyone's head must point in the same direction through space. The body only needs to align with the direction of gravity at its location. The feet point toward the ground, while the head points away from the center of the planet. The ideas of top and bottom largely come from the way humans draw maps. We usually place north at the top and south at the bottom, but this is only a convention. Turning a map upside down does not change anyone's posture or cause them to begin falling into the sky. Earth also has no required orientation in space. A spacecraft can view the planet from any angle. The image can be rotated in many different directions, while the laws of physics remain unchanged. Even so, the true direction of down does not always point precisely toward Earth's geometric center. The planet's mass is not distributed perfectly evenly. Mountains, dense layers of material, oceans, and structures deep beneath the surface all cause tiny variations in the local gravitational field. For this reason, a plumb line naturally aligns itself with the direction of gravity where it is suspended. That direction may differ very slightly from a straight line leading to the geometric center. The difference is invisible to the naked eye, but precise geodetic instruments can measure it. Using measurements like these, scientists construct a reference surface known as the geoid. It can be imagined as the shape the average sea surface would take if water were allowed to spread across the continents and were influenced only by gravity and Earth's rotation. The geoid is not perfectly smooth. It rises slightly where gravity is stronger and dips where gravity is weaker. Illustrations often exaggerate these differences dramatically, making Earth appear distorted. The real planet remains nearly round. The raised and lowered regions simply allow us to see variations that are far too small for the human eye to notice. This shows that gravity does more than hold people on the ground. It also helps define vertical direction, elevation, and the actual shape of the sea surface. A building aligned with a plumb line is being oriented according to the local gravitational field, not towards some imaginary bottom of the universe. The oceans provide one of the clearest demonstrations of how gravity works on a sphere. Water does not flow toward a single lower part of Earth because every region of the ocean has its own downward direction. Each portion of water is pulled inward, while the seafloor prevents it from falling any deeper. As a result, water can surround the planet without walls holding it in at the edges. The sea appears flat when viewed from the shore because the visible section is so small. On a global scale, that surface curves around Earth. At this point, Earth's rotation raises another question. If the planet is spinning, should people in the oceans not be thrown outward? A spinning amusement park ride makes this question seem reasonable. When the ride turns rapidly, the body is pressed against the side of the seat, and riders may feel as though they are being pushed away from the center. From that experience, it is easy to imagine Earth trying to fling everything into space, while gravity only barely holds it in place. In reality, the two effects are nowhere close to being balanced. The effect of rotation is strongest at the equator, but even there, it reduces effective gravitational acceleration by only about 0.35%. In other words, rotation lowers weight by only a very small amount. Gravity remains hundreds of times stronger than this effect. As you move toward the poles, the influence of rotation becomes weaker. The equator lies farthest from the axis and therefore travels around the largest circle each day. Near the poles, the path becomes smaller. Directly on the axis of rotation, a person almost turns in place, so the outward effect is nearly zero. Rotation does, however, leave a visible mark on the planet's shape. Earth is not a perfect sphere. It bulges slightly at the equator and is slightly flattened at the poles. The distance from Earth's center to the equator is nearly 13 miles, or about 21 kilometers, greater than the distance from the center to the poles. Compared with Earth's total size, this difference is very small. Even so, it is greater than the height of two Mount Everests stacked on top of each other. This bulge does not mean that rock and soil are close to being thrown off the planet. Over immense spans of time, Earth's material has redistributed itself under the combined influence of gravity and rotation. The planet has reached a balanced shape that is slightly wider around its middle. This shape also means that a person at the equator is farther from Earth's center than someone near a pole. The greater distance makes gravity slightly weaker. At the same time, rotation at the equator further reduces effective weight by a small amount. Because of these two effects, an extremely precise scale would give different readings for the same object measured at the equator and near the poles. The object's mass would not change, but its measured weight could be slightly greater in the polar regions. This is why mass and weight are not exactly the same. Mass describes the amount of matter in an object and its resistance to changes in motion. Weight is the force a body exerts on the surface, supporting it within a particular gravitational field. Altitude also creates a difference. When standing on a mountain, the body is farther from the center of the planet, so gravity becomes slightly weaker. Geological structures below the surface can also make the local gravitational field a little stronger or weaker. Modern instruments are sensitive enough to detect these variations, and can even track large-scale movements of groundwater or ice. Although gravity is not exactly the same everywhere, these variations are only minor adjustments. At every location on Earth's surface, gravity remains strong enough to hold people, buildings, and oceans to the planet. Familiar images from the International Space Station can sometimes make this more difficult to understand. In footage from orbit, astronauts float through the cabin, drops of water form spheres, and objects can hover in front of them. The scene easily creates the impression that gravity has disappeared. In reality, at the station's altitude, gravity is still nearly 90% as strong as it is at Earth's surface. Astronauts do not float because they have reached a place without gravity. They float because the station, their bodies, and everything inside it are falling freely around Earth together. The station moves sideways fast enough that as it falls toward the planet, Earth's curved surface continuously drops away beneath it. It is always falling, but it never reaches the ground. This prolonged fall is what we call an orbit. Inside the station, everything falls almost together, so there is no floor continuously supporting the body. As a result, astronauts experience weightlessness, even though gravity is still acting strongly upon them. On the ground, the body is also pulled by gravity, but it is not allowed to fall freely. The floor stops the downward motion. Matter in the floor pushes upward against the feet, and this supporting force is what creates the sensation of weight. A scale inside an elevator can reveal the difference. When the elevator is stationary, the scale measures the force with which the floor supports the body. If the elevator accelerates upward, the reading temporarily increases. When it accelerates downward, the reading decreases. Inside an ideal freely falling cabin, the scale could read nearly zero, even though gravity is still pulling both the person and the cabin downward. The sensation of weight, then, is not simply a direct sensation of gravity. It appears when a surface prevents the body from following its natural falling motion. On Earth, the ground performs this role day and night. After half a rotation, a person's body is facing an entirely different direction in space. Yet there is never a moment when they feel themselves being turned upside down. Gravity continues pulling their feet toward the center, the ground continues providing support, and the inner ear continues receiving a stable sense of downward direction. There is no hidden boundary where someone crosses from the top to the bottom of Earth. No one lives beneath the planet. Each person simply stands on a different part of its surface, with down defined by gravity at that location. Earth's rotation slightly reduces weight and contributes to the planet's equatorial bulge, but it comes nowhere close to throwing people into space. Gravity keeps our bodies, the rocks beneath us, and the entire ocean bound to the planet. The atmosphere, however, presents a more difficult question. Air is not a solid layer fixed firmly to the ground. Gas molecules are constantly moving, warm air can rise, and winds can travel across enormous distances. If Earth is rotating so quickly, why does the surface not slide beneath a layer of air left behind in space? Why does every day not begin with a wind more powerful than any storm? Gravity keeps the atmosphere close to the planet, but that is only half the answer. The other half lies in one important fact. The air is moving with Earth as well. If the air remained motionless in space while Earth rotated beneath it, every morning would begin with a catastrophe. Near the equator, the ground is moving eastward at more than 1,000 miles per hour, or roughly 1,600 kilometers per hour. Anyone standing on the surface would face an opposing flow of air, faster than many of the most powerful storms and, under ordinary conditions, even faster than the speed of sound. Reality is entirely different. On a calm day, leaves may barely move. Smoke rises slowly from a chimney. Birds can still take off in any direction, and a person can stand outside without being knocked down by an immense rush of air. This does not mean Earth is rotating more slowly than the numbers suggest. It means the original assumption was wrong. The atmosphere is not standing still while the planet spins through it. The air is also being carried eastward. The atmosphere is a layer of gas held around Earth by gravity. It does not form a rigid shell, but neither is it simply a cloud that happens to drift near the planet. Every molecule of gas has mass and is affected by gravity. As a result, most of the air remains concentrated near the surface instead of dispersing entirely into space. NASA describes the atmosphere as an extremely thin layer compared with the full size of the planet. If Earth were reduced to the size of a ball, the air that sustains life would resemble only a very thin coating around its surface. Gravity keeps the atmosphere close to Earth, but it does not by itself explain why the air rotates with the ground. To understand the rest, we must remember that velocity does not simply disappear when something leaves the surface. A molecule of gas, a bird, or an airplane already carries the planet's rotational motion before it begins moving in its own way. Return for a moment to a train traveling at a steady speed. The air inside the carriage does not collect at the rear. A fly can still move from one row of seats to another. If it takes off straight upward, the train does not race out from beneath it and leave the fly behind. Before leaving the seat, the fly was already moving with the train. The air inside the carriage shared the same velocity. Once airborne, the fly continues moving forward while using its wings to change position relative to the surrounding air. To a passenger, it is simply flying slowly through the carriage. To someone standing beside the tracks, the fly, the train, and the air inside are all rushing forward together. A person standing on Earth is in a similar situation. Before jumping, the body is already moving eastward with the surface. The moment both feet leave the ground, that velocity does not vanish. The jumper continues to be carried along while in the air and lands close to the place they left. If Earth truly rotated beneath a stationary atmosphere, even a brief jump would become dangerous. During a single second in the air, the ground near the equator could move hundreds of meters eastward. The jumper would land far to the west. Nothing like this happens because both the body and the surrounding air already share Earth's rotational velocity. The same question is often asked about helicopters. Why can a helicopter not rise into the air, remain stationary for several hours, and wait for another city to rotate beneath it? Just before takeoff, the helicopter is already moving with the ground. The surrounding air is also rotating with the planet. When the aircraft leaves the runway, it does not lose that eastward velocity. It only changes position relative to the air mass and the nearby surface. To reach another place, the helicopter must still fly across the distance between the two locations. It cannot remain motionless in some absolute space while the continent slides beneath it. Hot air balloons and weather balloons do not escape this principle either. When released, they already carry the rotational velocity of their launch site. Their later paths are governed mainly by winds at different altitudes. A balloon may drift hundreds or thousands of miles, but it does so because air currents carry it relative to the ground, not because Earth rotates away beneath it. The atmosphere therefore does not need to be pulled from rest at the beginning of each new day. It has shared the planet's rotation for an immense span of time. Land, oceans, and air form a connected system that constantly exchanges motion. Gas molecules collide with one another. The lower atmosphere interacts with trees, buildings, mountains, and bodies of water, and air currents at higher altitudes transfer motion to neighboring layers. Friction plays an important role near the surface. As wind moves across forests, cities, or rough terrain, its motion is slowed and altered. The oceans also exchange momentum with the atmosphere through the movement of waves. Air pushes against the water pushes back, and mountain ranges can force air currents upward, split them apart, or redirect their flow. Still, saying that the air rotates with Earth does not mean the entire atmosphere behaves like a solid object. A spinning metal disk forces all its parts to remain fixed relative to one another. The atmosphere is different. It is a fluid, constantly changing, able to flow across continents, rise, sink, and form weather systems thousands of miles wide. In some places, the air moves eastward faster than the surface. Elsewhere, it moves more slowly or drifts westward relative to the ground. High-altitude jet streams can reach speeds of hundreds of miles per hour, while the air near the surface at the same time may be almost completely calm. All these motions take place within an atmosphere that already carries the planet's shared rotational velocity. The difference between these two kinds of velocity is important. A person standing outdoors does not feel the speed of the air relative to distant stars. Skin, hair, and leaves respond only to the speed of the air relative to the local ground. When a weather forecast says the wind is blowing at 20 miles per hour, that number describes the air's movement relative to the surface, not its absolute velocity through space. A calm day does not mean the gas molecules are motionless. They move randomly in every direction because of heat, collide with one another constantly, and are carried around Earth's axis at the same time. Calm simply means that the organized motion of the air relative to an observer on the ground is fairly small. Aviation must distinguish very carefully between these different velocities. An airplane has one speed relative to the air mass around it, and another relative to the ground. With a strong tailwind, the aircraft may reach its destination sooner, even though its engines and airspeed remain unchanged. With a headwind, the journey takes longer because the surrounding air is moving in an unfavorable direction relative to the surface. Passengers inside the cabin do not feel the aircraft's full speed over the ground. Their bodies mainly notice turbulence, changes in altitude, or acceleration. In the same way, people on Earth do not feel the rotational velocity shared by the atmosphere and the ground. We sense only the remaining motion between the air and our bodies, the part we call wind. Another practical piece of evidence comes from aerospace engineering. Many rockets are launched eastward to take advantage of the rotational velocity they already possess while still standing on the launch pad. Near the equator, this free contribution can exceed 1,000 miles per hour, helping the rocket use less fuel to reach orbit or allowing it to carry a heavier payload. The rocket, the launch pad, and the surrounding air all begin with eastward motion. During the first seconds of flight, the rocket does not have to accelerate from absolute rest in space. It was already moving with Earth before its engines ignited. As it rises, the engines add new velocity to the motion it already carries. This detail also shows that the planet's rotational speed is real, even though we do not feel it in daily life. It can be calculated, measured, and used to conserve fuel during journeys into space. Yet because the ground and the lower atmosphere share most of that velocity, Earth's rotation alone does not create winds of more than 1,000 miles per hour. The atmosphere is also far more concentrated near the ground than the open sky might suggest. About 80% of its mass lies within its lowest layer, the troposphere, which has an average thickness of only about 7.5 miles, or 12 kilometers. Nearly all the water vapor, clouds, and familiar weather are also concentrated within this relatively thin region. At greater altitudes, density and pressure decrease rapidly. About 99% of the atmosphere's mass lies below an altitude of approximately 20 miles, or 32 kilometers. The remaining 1% is spread very thinly across hundreds of kilometers above. This creates a striking image. When we look upward, the atmosphere seems almost endless. Yet nearly all the air that creates weather, supports aircraft, and sustains life is contained within a layer thinner than the distance of a short trip across the ground. Air pressure is the weight of the atmosphere above us. At sea level, the atmosphere produces an average pressure of about 14.7 pounds per square inch. The body is not crushed because the fluids and gases inside it also exert outward pressure, helping to balance the force from outside. When we climb a high mountain or travel in an airplane, there is less air above us, so the pressure becomes lower. Aircraft cabins must be pressurized because, at cruising altitude, the outside air is too thin for people to breathe normally. This shows that the atmosphere is not held around Earth as a layer of uniform density. Gravity compresses most of its mass close to the surface. At its upper edge, the atmosphere does not end at a clearly defined wall. The air simply becomes thinner and thinner until molecules can travel great distances without frequently colliding with one another. A small number of particles in the outermost regions reach conditions that allow them to escape Earth, but this process does not cause the entire atmosphere to disappear quickly. Most molecules at lower altitudes remain bound by gravity and continue colliding with the particles around them. The upper atmosphere also does not necessarily rotate at exactly the same speed as the ground at every moment. Energy from the sun, changes in temperature, electric currents in the upper layers, and many other processes can produce complex movements. But the mass at these altitudes is extremely small compared with the dense air below, so these motions do not create enormous winds at the surface. The atmosphere even exchanges a very small amount of rotational motion with the solid planet. When global wind systems change, the amount of rotational momentum stored in the atmosphere changes as well. Earth responds with extremely small variations in its rotation rate, subtle enough to be detected by precise timekeeping measurements. NASA has observed a connection between atmospheric angular momentum and slight changes in the length of the day. The atmosphere, then, is not merely a passive passenger. It constantly exchanges motion with the oceans and the solid ground below. When winds accelerate across a vast region, that momentum must come from somewhere else within the system. These changes are far too small to affect the clocks in our homes, but they reveal that the atmosphere and the planet are connected far more deeply than a layer of gas that merely happens to surround the surface. Imagine once again the fly inside the moving train. It can fly forward, backward, or sideways relative to the seats. No one would say that it is rigidly attached to the train. Yet every motion of its own takes place on top of the shared velocity already carried by the train, the air, and the fly itself. The atmosphere behaves in the same way. Air may move against the direction of rotation relative to the local ground, but it does not begin from rest in space. A westward wind is still being carried eastward by the planet when measured against a distant reference point. It is simply moving eastward more slowly than the surface beneath it. Conversely, an eastward air current may move faster than the ground. What people feel is the difference between those two motions. No sensory receptor in the skin can separate the shared velocity of the entire system from the relative velocity of the wind. For this reason, the statement that the atmosphere rotates with Earth must be understood carefully. The air is not locked to every field or ocean. It does not rotate like a rigid coat of paint covering the planet. More precisely, most of the atmosphere already carries Earth's shared rotational motion, while winds and weather are movements that develop within that broader motion. The stillness of a calm day is not evidence that the air is motionless in the universe. On the contrary, every breath is traveling around Earth's axis together with the listener, the room, and the entire planet at tremendous speed. We do not feel that portion of the velocity because the air near the ground is not rushing past our bodies. It is sharing the journey, but the atmosphere is clearly never completely still. Sea breezes appear in the afternoon. Cold air moves down from higher latitudes. Jet streams curve around the planet, while storms can rotate and travel across the oceans. If wind is not created because Earth spins through a stationary layer of air, then what actually causes the atmosphere to begin moving? The answer lies not primarily in the planet's rotational speed, but in the way the sun heats Earth's surface unevenly. From seemingly small differences in temperature and pressure, the planet's entire system of winds begins to form. On a nearly windless day, the ground beneath your feet is still racing eastward at tremendous speed. Yet smoke from a chimney may rise almost straight upward, the surface of a lake may remain smooth, and leaves may barely tremble. If Earth were truly spinning through a stationary layer of air, such a scene could not exist. Every place on the planet would endure a violent wind blowing continuously in the same direction. The atmosphere is not being left behind. It already carries most of the planet's rotational motion. For this reason, the surface speed of more than 1,000 miles per hour near the equator does not automatically become the wind speed felt by the body. Wind appears only when one part of the air moves differently from the surrounding air or the surface below. What creates that difference? The answer begins with the sun, but not because sunlight pushes the air like an invisible hand. Solar energy warms Earth's surface, and the surface then transfers heat to the air near it. The important point is that this process does not happen equally everywhere. Regions near the equator generally receive more direct sunlight than areas near the poles. The same amount of energy is concentrated over a smaller area, causing the surface at lower latitudes to be heated more strongly overall. Closer to the poles, sunlight arrives at a lower angle, spreading its energy across a wider region. Even within the same area, temperatures are not uniform. Land warms more quickly than the ocean during the day, but it also loses heat more rapidly after sunset. A rocky surface, a field, a forest, and a body of water can all reach different temperatures even beneath the same sky. Cities create another kind of contrast. Concrete, asphalt, and buildings absorb heat and retain it longer than the surrounding vegetation. A desert responds to sunlight differently from the ocean. A mountain slope facing the sun may become noticeably warmer than one lying in shadow. Because of millions of differences like these, the atmosphere rarely reaches complete balance. The air is warmer in some places and colder in others. One region may contain a dense, heavy air mass, while nearby air is expanding and rising. This imbalance is what sets the atmosphere in motion. When heated, air expands and usually becomes less dense. A warm air mass does not necessarily rise immediately like a balloon, but if it is lighter than the surrounding air, buoyancy can begin lifting it upward. As air leaves the lower atmosphere, the amount of air directly above the surface decreases, and the pressure there tends to fall. In a colder region, the air is often denser and may sink. As more air accumulates near the ground, pressure rises. The difference between high pressure and low pressure regions creates a force that begins pushing the air into motion. It is often said that wind blows from high pressure toward low pressure. This is correct at a basic level, but the actual movement is more complex. Pressure differences provide the initial driving force, while terrain, friction, temperature, and Earth's rotation continually modify the path of the moving air. Pressure can be imagined as the weight of the column of air above a region. Where more atmospheric mass is present overhead, pressure is generally higher. When this distribution becomes uneven, the atmosphere attempts to adjust by moving air from one region to another. If the pressure difference is small, the wind may be gentle. When pressure changes sharply over a short distance, the force driving the air is greater, and winds tend to become stronger. On weather maps, lines connecting points of equal pressure are called isobars. When these lines are packed closely together, they usually indicate a region with a strong pressure gradient and the potential for powerful winds. A familiar example appears along the coast each afternoon. During the day, the land absorbs heat and warms more quickly than the water. The air near the ground also heats up, expands, and begins to rise. Surface pressure over the land becomes relatively lower than it is over the sea. Above the water, temperatures remain cooler and the air stays denser. This cooler air begins moving toward the shore to replace the air rising over the land. A person standing near the coast feels a breeze coming in from the sea, even though the air may have been almost completely still earlier that morning. This breeze does not appear because the coastline is rotating through the atmosphere. The land, the ocean, and the air are all taking part in Earth's shared motion. A sea breeze forms because of differences in temperature and pressure between two surfaces that are heated in different ways. After sunset, the process can reverse. The land loses heat more quickly than the ocean, while the water retains warmth for longer. The air over the sea may then become warmer and rise, while cooler air from the land moves outward over the water. A land breeze is usually weaker than a sea breeze, but it shows how wind direction can change simply because heat is stored differently through day and night. Another version of this process takes place on mountain slopes. During the day, sunlight warms the slope, causing the nearby air to move upward. At night, the surface cools quickly, making the air colder and denser so that it flows down into the valley. These local winds form without any change in the planet's rotational speed. On a larger scale, the temperature difference between the equator and the poles provides energy for the global circulation system. Warm air at low latitudes tends to rise, move through the upper atmosphere, and gradually lose heat. In other regions, air sinks and returns closer to the surface. If Earth did not rotate, the global pattern might be much simpler. Warm air would tend to rise near the equator, flow toward the poles high in the atmosphere, cool and sink, then return toward the equator near the surface. But the planet is rotating, so moving air cannot follow perfectly straight north-south paths. When air begins traveling across great distances, Earth's rotation makes its path appear to curve from the perspective of someone standing on the surface. This influence is known as the Coriolis effect. It does not necessarily create the initial wind, but it can alter the direction of the air after that motion has begun. Imagine a stream of air being pushed from a region of high pressure toward an area of low pressure. Over the first few miles, the deflection may be extremely small, but when the journey continues across hundreds or thousands of miles, those tiny changes accumulate, and the path no longer resembles a straight line. In the northern hemisphere, motion generally appears to curve toward the right of its direction of travel. In the southern hemisphere, it appears to curve toward the left. This difference is not caused by the air encountering an invisible wall. It appears because the observer is standing on a rotating surface, while regions at different latitudes have different linear velocities. A more complete explanation of the Coriolis effect will come in a later chapter. For now, the important point is its role. Differences in temperature and pressure set the air in motion. While Earth's rotation helps curve its path and organize large-scale atmospheric flows, friction continues to alter the picture. Near the ground, air encounters trees, buildings, ocean waves, and uneven terrain. These obstacles slow the wind, create small eddies, and cause its direction to differ from that of the air higher above. A wind crossing an open plain may maintain its speed more easily than when it enters a city or a dense forest. Mountain ranges force air to rise, move around them, or divide into separate streams. As air is lifted, it cools, allowing water vapor to condense and form clouds or rain. On the far side of a mountain, descending air may become warmer and drier. A single mountain range can create major differences between two regions that are not very far apart. This shows that wind is not simply air moving from one pressure reading toward another. It is constantly responding to the surface below. The oceans are also part of the system. Wind transfers motion to the water, creating waves and helping drive ocean currents. In return, sea surface temperatures influence the air above, changing humidity, pressure, and the conditions that allow storms to form. The atmosphere and the oceans are not separate systems. They exchange heat, water vapor, and momentum day and night. A change at the ocean's surface can affect weather thousands of miles away, while wind patterns lasting for months can also redistribute heat within the sea. Higher in the atmosphere, where friction with the ground is weaker, air can reach tremendous speeds. Near the boundary between the troposphere and the layer above are narrow bands of powerful wind known as jet streams. They usually meander around the planet rather than forming perfect circles. Jet streams become especially strong where large temperature differences exist between air masses. Warm and cold air create differences in pressure with altitude, while Earth's rotation organizes the winds into a mainly west to east flow across the middle latitudes. The average speed of a jet stream may be around 110 miles per hour, or nearly 180 kilometers per hour. During periods of especially strong temperature contrast, some sections may exceed 250 miles per hour, or more than 400 kilometers per hour. That is an enormous speed, great enough to noticeably affect the duration of long-distance flights. An aircraft traveling in the same direction as the jet stream may arrive earlier, while one flying against it may take longer or follow a different route. Even so, the jet stream is not evidence that the upper atmosphere is being left behind by the rotating Earth. It is a current moving within an atmosphere that is already rotating with the planet. Its speed is measured relative to the ground or other air masses, not relative to some state of absolute rest in space. An air current blowing westward may still be moving eastward when viewed from a distant reference point. It is simply traveling eastward more slowly than the surface below. Likewise, an eastward wind means the air mass is moving ahead of the ground in that direction. What people feel is always the difference between these motions. The skin does not detect the rotational velocity shared by Earth and its atmosphere. It senses only how quickly the air is passing over the body. This is why a calm day can exist on a rapidly rotating planet. This distinction also helps explain why wind direction changes constantly. If wind were merely the result of Earth rotating beneath a stationary atmosphere, it would have to blow in almost the same direction everywhere and at all times. In reality, wind can reverse within a few hours, blow from the sea during the day and from the land at night, or change completely when a pressure system passes through. Sometimes, two layers of air above the same location may even move in different directions. Winds near the surface may be gentle, while a few miles higher, the flow is already powerful. One layer may move northward, while another drifts eastward. This vertical structure reflects differences in temperature, pressure, and friction throughout the atmosphere. Weather forecasting therefore requires data from many altitudes. Ground stations measure temperature, pressure, and winds near the surface. Weather balloons carry instruments upward to record changes through the atmosphere. Satellites monitor clouds, water vapor, and temperature across the entire planet. From these measurements, meteorologists ask more than simply which direction the wind is blowing. They must understand what is creating the pressure differences, how the airflow is being curved, how terrain will alter it, and at what altitudes different air masses are interacting. A gentle breeze across a porch and a jet stream stretching thousands of miles follow the same basic principle. Air moves because the atmosphere has been pushed out of balance. Solar energy heats the surface unevenly, temperature alters density and pressure, and the atmosphere responds by shifting mass from one region to another. Earth's rotation does not have to create the initial imbalance. It enters the story afterward, curving long-distance paths, helping organize wind belts, and influencing the direction of large weather systems. In other words, the sun supplies most of the energy. Pressure differences provide the driving force, terrain and friction reshape the flow, and Earth's rotation curves its path. None of these factors acts entirely alone. Weather emerges from the interaction of them all. Wind, then, is not the roar of a planet spinning through motionless air. It is the internal movement of a dynamic atmosphere, continually working to redistribute heat and mass across a surface warmed unevenly by the sunday. An afternoon sea breeze may begin with only a few degrees of difference between land and water. A current high in the atmosphere may strengthen when warm and cold air masses lie beside one another. Larger systems form when these contrasts persist, and Earth's rotation bends their paths around the planet. The naked eye can see trees bending, clouds drifting, and waves rising, but it cannot directly see Earth rotating through the atmosphere. The shared motion is too steady, and is carried by both the ground and most of the air. To see the planet turning, we need a background that is not taking part in the same journey. It must be distant enough that the ground cannot carry it along, yet bright enough to reveal changes over many hours. Long before humans possessed precise clocks, the night sky provided that background. The stars do not remain fixed in one place. They quietly rise, cross the sky, and set again, night after night, leaving behind traces of the motion unfolding beneath our feet. If you look up at the sky for only a few seconds, the stars appear completely motionless. They seem to remain in exactly the same places when you look again a minute later, and even after 10 minutes, any change is difficult to notice. But place a camera on a fixed tripod, point its lens toward the sky, and leave the shutter open for several hours. The resulting image will reveal a motion that the human eye is not patient enough to see. The stars no longer appear as individual points of light. Each one stretches into a curved line, and hundreds of these curves together form enormous circles across the sky. Bright stars leave stronger trails, while dimmer stars produce finer ones, but nearly all of them follow the same rhythm. The sky that seemed motionless has been quietly changing throughout the camera's observation. The longer the exposure, the longer the trails become. A brief exposure produces only short marks, almost like dashes. After several hours, they extend into distinct arcs. If darkness could last long enough for the camera to record nearly an entire rotation, many of the star trails would almost close into complete circles. A question immediately appears: what is actually rotating? At first glance, the photograph seems to show the entire sky turning around Earth. This was also the conclusion people once reached by observing the sun, moon, and stars with the naked eye. But just as trees appear to rush backward past the window of a moving train, the motion seen in the sky may be created by the observer's own movement. The camera is fixed to the ground. The tripod, the field, the mountain, and the person standing beside it are all rotating with the planet. As Earth turns from west to east, the lens continually changes its direction in space. The stars therefore appear to drift westward, leaving curved trails of light across the camera's sensor. The camera does not directly photograph Earth rotating. It records how the ground's viewing direction changes relative to the extremely distant stars. In other words, The trails are traces of the relative motion between the observer and the sky. A star trail photograph alone is not the only piece of evidence capable of distinguishing between every possible model of motion. Yet, when combined with other observations, it transforms a movement too slow for the senses into a clear image. The ground appears still from moment to moment, but after several hours, it has changed direction enough for the sky to draw hundreds of curves. A particularly striking detail appears when the camera is pointed north. The star trails do not move randomly. They seem to circle around a common point. The closer a star lies to that point, the smaller its circle becomes. The farther away it is, the wider its arc appears. Near the center of these circles lies Polaris, commonly known as the North Star. Polaris appears almost motionless while the rest of the sky turns around it. This is not because the star is closer to Earth or because it does not move through space. The reason lies in the direction of the planet's rotational axis. Imagine extending Earth's axis outward from the North Pole and continuing that line into the sky. The direction it points toward is called the North Celestial Pole. As the planet rotates, the orientation of its axis remains nearly stable over the course of a single night. So this point in the sky appears not to change position. Polaris lies fairly close to the North Celestial Pole, so it traces only a small circle. It is not positioned exactly on the axis, which means that with sensitive equipment and enough observing time, the star can still be seen drawing a small arc around the pole. To the naked eye, however, this movement is so slight that Polaris appears almost stationary. Stars farther from the North Celestial Pole create larger circles. The entire sky can be imagined as an enormous disk rotating around a pin located near Polaris. The pin remains almost still, while points farther from the center travel along much longer paths. This image also explains why the North Star once played such an important role in navigation. Although the sky changes throughout the night, Polaris remains close to the northern direction. An observer does not need to know the exact time to use it as a reference because it does not rise in the east and set in the west like most other stars. Polaris, however, is not a real pin holding the sky in place. It simply happens to lie near the direction in which Earth's northern rotational axis points during the present era. The planet's axis changes direction very slowly over long periods of time, so in the distant past and distant future, other stars may lie closer to the celestial pole. Over the course of a human lifetime, this change is far too slow to affect an ordinary night of observation. Polaris remains a convenient guide, and the star trails continue circling the region near it. What matters is not how special the star itself may be, but that it lies close to the extension of Earth's axis. In the southern hemisphere, the sky has a corresponding point of rotation. Earth's axis extends through the South Pole and points toward the South Celestial Pole. The stars there also trace circles around a shared center. But unlike the northern sky, no bright and prominent star lies close to the pole in the way Polaris does. Observers in the southern hemisphere therefore often rely on the shapes of constellations or other navigational methods to estimate the location of the celestial pole. Even without a clearly visible marker star, long exposure photographs reveal the same structure, concentric arcs of light revolving around the direction of Earth's axis. The apparent direction of the sky's rotation also changes depending on the hemisphere. When facing the North Celestial Pole, the star trails appear to turn in one direction. When facing the South Celestial Pole, they seem to turn the opposite way. This is not because the two halves of the sky are truly rotating against each other, but because observers are viewing the same planetary rotation from opposite sides. An observer's position on Earth also determines the angle of the star circles. Near a geographic pole, the celestial pole appears high overhead. The stars therefore seem to travel in circles nearly parallel to the horizon, and many may never rise or set during the night, continuing instead to revolve around the sky. A star that never passes below the horizon at a particular latitude is called a circumpolar star. Its position still changes, but its entire apparent path remains above the horizon. The closer an observer moves toward a pole, the greater the number of stars that can be seen in this way. At the geographic pole itself, the celestial pole would appear almost directly overhead. An observer there would see the stars moving in horizontal circles around the sky. They would not rise at an angle and quickly set as they do in many other places. Instead, Each star would remain at nearly the same altitude while circling around the observer. As one moves away from the pole toward lower latitudes, the celestial pole gradually descends toward the horizon. The star circles tilt with it. Some stars begin to rise on one side of the sky, travel along an arc, and set on the opposite side. Near the equator, the two celestial poles lie close to the horizon in the north and south. Many stars then follow more upright apparent paths, rising quickly above the eastern horizon before descending in the west. The sky continues to rotate at the same rhythm, but the shape of its motion changes with the observer's location. This is one of the ways the sky reveals that Earth is not an endlessly wide, flat surface. If everyone stood beneath the same flat dome, the motion of the stars could hardly change so systematically with latitude. On a spherical planet, each person views the rotational axis from a different angle, so the arcs traced by the stars change as well. As someone travels north, Polaris appears higher above the horizon. Moving south, the star sinks lower. The altitude of the north celestial pole above the horizon roughly corresponds to the observer's latitude, a relationship that helped people estimate their position long before satellite navigation existed. The sky, then, was more than a clock. It was also a navigational tool. The positions of the stars revealed north and south. Their movement helped measure the passing hours of the night, and their seasonal changes helped identify the time of year. But to see this clock running, people had to be patient. In a brief moment, each star looks like a motionless dot of ink. An hour later, that dot has shifted to another position. When an entire night is compressed into a single photograph, the separate points join together into glowing circles. Earth rotates at a relatively steady rate, so the sky appears to move by nearly 15 degrees each hour. This is the same apparent motion mentioned earlier when observing the sun during the day. After about 4 hours, a star has traveled along an arc of nearly 60 degrees, or 1/6 of a full circle. To the naked eye, this change is usually noticed only when there is a clear reference point. A star may begin the night above the top of a tree and drift elsewhere several hours later. A constellation that has just appeared near the horizon may be much higher when the observer looks again. The camera performs this comparison in place of human memory. It records light continuously on the same image, preserving every position through which a star has passed. Time is no longer a series of separate moments. It becomes a line of light. Relative to the distant stars, Earth completes one rotation in approximately 23 hours, 56 minutes, and 4 seconds. This interval is known as a sidereal day. It is about 4 minutes shorter than the 24-hour day used in everyday life. The difference appears because Earth is also traveling around the Sun while rotating on its axis. After completing one turn relative to the distant stars, the planet must rotate through a small additional angle for the Sun to return to nearly the same position in the sky. That extra rotation makes the solar day close to 24 hours long. A later chapter about time will return to this difference in greater detail. In the night sky, its most visible consequence is that the stars appear about 4 minutes earlier each day. A constellation occupying a particular position at a certain time tonight will reach that same position slightly earlier tomorrow night. 4 minutes may seem insignificant, but as those minutes accumulate over several weeks, constellations that once appeared late at night gradually become visible earlier. The sky of one season therefore differs from the sky several months later, not only because of the weather, but also because Earth's position in its orbit around the Sun has changed. Over the course of a single night, however, Earth's rotation remains the dominant motion. Each hour, the ground turns through another angle. The camera changes direction with the planet. The stars leave behind steady arcs of light, like minute marks on a clock as large as the entire sky. The regularity of these curves is also important. If Earth accelerated and slowed dramatically during the night, the distribution of light along the star trails would change noticeably. Instead, the arcs usually appear smooth and continuous, reflecting a stable rotation over the period of observation. A modern camera can create such an image in a single night, but people recognized the movement of the stars thousands of years ago. They did not need electronic sensors to notice that the points of light rose and set according to a repeating rhythm. Ancient structures, agricultural calendars, and methods of navigation all relied on the stability of the sky. Even so, direct experience preserves the old illusion. Standing beneath the star trails, the observer does not feel the ground turning. The grass beneath their feet does not shift, the camera tripod does not tilt, and the horizon keeps the same shape. The sky still seems to be the part that is moving. This is one of the limitations of living inside a rotating system. The camera, the observer, and the ground all change direction together, so nothing nearby provides a stationary reference point. Only the distant stars make this shared motion visible. If we imagine watching from outside Earth, the interpretation reverses. The stars maintain nearly the same directions during the course of a single night. While the planet rotates beneath them, a point on the surface turns toward different regions of the sky one after another, making the person standing there feel as though the stars are circling around them. Both descriptions reflect relative motion, but the physics of the planet allows us to determine that Earth is rotating around its axis. Measurements involving pendulums, the Coriolis effect, the equatorial bulge, and many other phenomena all support the same conclusion. Star trails, therefore, do not stand alone as the only evidence. They are one part of a much larger picture, while also being among its most visible features. There is no need to feel a speed of more than 1,000 miles per hour. We need only allow time to accumulate light, and the invisible motion will draw its own shape. Each glowing line is the trail of a star, but it is also the trail of a changing line of sight. Every circle in the sky reflects a rotation beneath the ground. The region near Polaris serves as the center of the clock, while stars farther away create increasingly wider rings that mark the passing hours. The sky does not need to move quickly to reveal that the observer is in motion. It only needs to be distant, stable, and watched for long enough. For a few seconds, nothing seems to happen. After several hours, the entire celestial dome has become a system of circles. When the shutter finally closes, the camera is still standing exactly where it began. The observer has not stepped away from their position, yet during that time, the ground has changed its orientation enormously relative to every star in the frame. The photograph preserves a journey the body never felt. The stars have provided a background beyond the shared rotation of the ground. Through them, people can see the traces of the planet as though observing it from the outside. But is it possible to prove that Earth is rotating without looking at the sun, the moon, or any star at all? One experiment can do exactly that inside a building. All it requires is a long wire, a heavy weight, and enough time for the stone floor that seems perfectly still to reveal that it is turning beneath the observer's feet. Imagine entering a vast, quiet building. From the high ceiling above, a very long wire descends almost to the floor, carrying a large weight at its lower end. The weight moves slowly through the center of the room, travels toward the opposite side, pauses for a moment, and then returns along nearly the same path. During the first few minutes, the scene looks like nothing more than an ordinary pendulum swinging under the influence of gravity, with no sign that the motion of an entire planet is being revealed before your eyes. But if the original direction of the swing is marked on the floor, and you return several hours later, something unusual will appear. The weight continues moving back and forth at almost the same rhythm, yet its path no longer aligns with the original mark. If a ring of small pegs surrounds the pendulum, the weight will gradually knock them down one after another, as though the plane of its swing were slowly rotating through the room. At first, an observer might assume that the pendulum itself has changed direction. The suspension point may be misaligned, the wire may be twisted, or a faint current of air may have pushed the weight sideways. These factors can indeed introduce errors if the apparatus is not prepared carefully, but when the pendulum is suspended correctly and allowed to operate long enough, its steady change relative to the floor comes from a much larger cause. The building, the observer, and the entire ground beneath them are being carried by Earth, beneath the pendulum's plane of motion. In 1851, Léon Foucault transformed this principle into one of the clearest visual demonstrations of Earth's rotation. Instead of asking people to observe the sun or track the stars throughout the night, he used a large weight suspended from a long wire. As the pendulum continued to swing, its direction gradually changed relative to the room, allowing those watching to recognize that the surface appearing motionless beneath their feet was actually turning. The power of the experiment lies in its simplicity. It requires no telescope, no journey into space, and no complete reliance on the movement of celestial objects. A weight simply swings back and forth inside a room, while the stone floor quietly reveals its own changing orientation. The rotation of a planet thousands of kilometers wide is reduced to a slow shift visible among a few markers on the floor. To understand what is happening, imagine pulling a pendulum to one side and releasing it very carefully. Gravity brings the weight back toward its lowest point. Inertia carries it onward to the opposite side, and the process then repeats. If no sideways force interferes, the pendulum tends to preserve its original plane of oscillation rather than turning freely around its suspension point. The pendulum's suspension point remains attached to the building and is not completely separated from the planet. Even so, a sufficiently long and carefully designed pendulum can maintain a relatively stable direction of oscillation while the floor slowly changes orientation with Earth. The observer standing on the floor rotates with the room, so from their perspective, the pendulum appears to turn toward a new direction. From a reference frame that does not rotate with the ground, however, it is the building that is continually changing its orientation. The effect can be imagined as a sheet of paper slowly rotating beneath the tip of a pen moving back and forth. If the pen keeps pointing in the same direction while the paper turns, the lines drawn on the page will gradually change angle. Someone standing on the paper might think the pen is rotating, while an outside observer would recognize that the surface beneath it is changing direction. A Foucault pendulum creates a similar comparison between its plane of oscillation and the rotating ground. This effect is very slow, so the pendulum must continue operating for long enough before the change becomes obvious. The first few swings reveal almost nothing unusual. After hundreds and then thousands of passes, tiny shifts accumulate into an angle large enough for the eye to detect. The motion becomes visible in much the same way as star trails across the sky. Each individual moment appears almost unchanged, but several hours of observation allow the evidence of rotation to emerge. To achieve this stability, a Foucault pendulum usually uses a long wire and a heavy weight. A longer wire produces a slower period of oscillation, making the motion easier to follow, while a heavier weight is less affected by small air currents. Air resistance still causes the pendulum to lose energy over time, so many modern display installations use a mechanism that provides a very gentle impulse to maintain the swing without forcing the weight into a new direction. The method used to release the pendulum must also be carefully controlled. If someone pushes it by hand, even a small sideways force can send the weight into an elliptical path and obscure the effect being observed. Instead, the pendulum is usually drawn to one side, held motionless, and then released without receiving an additional sideways push. Gravity begins the movement on its own, while the initial direction of oscillation remains largely undisturbed by the experimenter's hand. One of the most interesting features of the Foucault pendulum is that the apparent rate at which its direction changes depends on latitude. The same apparatus placed at different locations on Earth will not sweep across the floor at the same pace. This pattern shows that the phenomenon does not arise solely from the suspension point, air currents inside the room, or the way the weight was released. It is directly connected to the geometry of a rotating planet. The easiest case to visualize occurs at either geographic pole. There, Earth's axis of rotation passes almost directly through the pendulum's location and stands perpendicular to the local floor. While the pendulum's plane of oscillation tends to preserve its direction, the ground beneath it completes a full rotation. To someone standing in the room, the direction of the swing can therefore sweep through a full 360 degrees in roughly one day. If a numbered ring like a clock face were placed around the pendulum, the weight might initially swing between 12 o'clock and 6 o'clock. After some time, its path would point closer to 1 o'clock and 7 o'clock, then continue shifting through the other directions. Viewed from the floor, the pendulum appears to rotate around the center. Viewed from outside the planet, the floor and all the numbered markers are completing a full turn beneath it. As the pendulum moves away from the poles, its apparent rate of rotation decreases. Earth's axis no longer passes through the local floor in the same way, so only part of the planet's rotation appears as a turning of the pendulum's plane around the local vertical. At middle latitudes, an observer must wait longer before the pendulum shifts by a clearly visible angle from its original mark. The closer the pendulum is brought to the equator, the slower this change becomes. At the equator itself, the apparent turning of the plane is nearly zero in the ideal model. The pendulum continues to swing. The ground continues moving rapidly around Earth's axis, and the planet still completes a full rotation, but the plane of oscillation does not sweep around the local vertical as it does near the poles. This does not mean the pendulum no longer reflects the rotation of the planet. The instrument does not directly measure the linear speed of the surface in kilometers per hour. It reveals how the local frame of reference rotates around the vertical at the pendulum's location. This component of motion is most pronounced at the poles, decreases with latitude, and nearly disappears at the equator. The effect can be compared to viewing a wheel from different angles. When looking directly along its axis, the circular motion is fully visible. If the observer shifts to another angle, the projected motion changes even though the wheel continues rotating at the same speed. The Foucault pendulum likewise produces a different appearance depending on how the local surface is positioned relative to Earth's rotational axis. When moving from the northern hemisphere to the southern hemisphere, the pendulum's apparent direction of rotation reverses. This does not mean the two halves of the planet rotate in opposite directions. Earth continues turning in only one direction, but observers are standing on opposite sides of the sphere and viewing the changing floor from opposing perspectives. This reversal further strengthens the connection between the pendulum and the planet's global rotation. A draft inside the room or a twisted wire would be unlikely to create a pattern that changes so precisely with latitude. Errors in the apparatus usually depend on the room, the suspension point, and the way the pendulum is operated. The Foucault effect, by contrast, is strongest near the poles, weakens toward the equator, and reverses direction between the hemispheres, exactly as predicted by the geometry of a rotating Earth. Even so, not every weight tied to a string can easily display this effect. A small pendulum may stop moving before the shift becomes visible. Vibrations from the floor, currents from an air conditioning system, or an uneven suspension point can produce errors larger than the signal being observed. For this reason, display pendulums are usually installed in large spaces, suspended from long wires, and carefully calibrated. A circle of pegs arranged around the floor transforms the passage of time into a physical record. The weight does not knock every peg down at once. It continues swinging back and forth until the relative motion between its plane of oscillation and the floor brings one peg into its path. Later, another peg is struck, followed by another, creating a sequence of evidence that the floor's orientation is slowly changing. Each fallen peg records a tiny part of the planet's rotation. The observer does not need to remember exactly which direction the pendulum was facing several hours earlier, because the gaps in the ring preserve that history. Earth's immense motion is divided into small events, each one no more than the gentle touch of the weight against an object resting on the floor. The paradox of the scene is that the weight is the object most visibly in motion, yet it serves as a relatively stable directional reference. The stone floor, the walls, and the people watching all appear motionless, even though they are the ones being carried through a continuous change by the planet. Each time the pendulum returns, the building has shifted its orientation in space by a very small amount. That change is too slight to notice during a single swing, but it does not disappear. The next swing adds another small amount, and the swings that follow continue the accumulation. Several hours later, the total shift has become large enough to see. The pendulum does not create Earth's motion. It simply maintains a reference stable enough for the shared movement of the room to stop being completely invisible. This also explains why the human body cannot sense the same rotation on its own. The eyes, inner ear, and muscles all move with the ground. There is no strong acceleration, no nearby scenery rushing past, and no independent direction maintained for hours against which the motion can be compared. The pendulum performs the role our senses cannot, preserving a plane of oscillation long enough for the difference between it and the building to emerge. In the middle of the 19th century, the power of this demonstration did not come from its being the first or only evidence that Earth rotates. The planet's motion had already been inferred from astronomy and many other phenomena. What was new was that people could enter a building, stand on a stone floor, and watch that very floor reveal its motion without having to observe the sky. Even with the windows closed, the sun below the horizon, and clouds hiding every star, the pendulum continues telling the same story. As long as the weight swings with sufficient stability, its direction gradually separates from the markers on the floor. The sky is no longer the only background against which people can recognize that they are standing on a rotating planet. Today, instruments using gyroscopes, beams of light, or atoms can measure rotation with far greater precision. Yet few devices present the phenomenon as clearly as a weight swinging back and forth through a room. The pendulum requires no speed display and no equations beside it. The observer needs only to watch the direction of the swing and the positions of the markers below. When the experiment begins, the two directions nearly coincide. As time passes, the separation between them slowly increases, and within that growing difference, the motion of the planet becomes visible. The ground does not suddenly tremble, nor does the building spin rapidly before the eye. Instead, a very small motion accumulates long enough to break the illusion of stillness. If Earth truly did not rotate, the regular change in direction produced by the Foucault effect would not appear. The pendulum might still drift because of wind, friction, or imperfections in the apparatus, but those changes would not follow the clear pattern of latitude and hemisphere. It is this systematic relationship with location on the planet that makes the experiment so convincing. At a pole, the ground can complete nearly one full rotation beneath the plane of oscillation in about a day. At middle latitudes, the process unfolds more slowly, while at the equator, the apparent turning around the local vertical nearly disappears. An instrument that seems remarkably simple can produce different results merely because it has been placed at different locations on the same sphere. Beneath the weight swinging back and forth, the floor retains its familiar appearance of solidity. No one feels the building turning, yet the markers below reveal that this sensation does not represent the whole motion. The room is stationary only relative to the observer, while both are continuously being reoriented in space by the planet. The Foucault pendulum transforms this rotation into a phenomenon that can be observed inside a room. Outside the building, however, Earth's motion leaves traces in systems far larger than any pendulum. Air can travel across an entire continent, while seawater can move around vast ocean basins. As masses of air and water travel from one latitude to another, they carry the velocity of the place where their journey began, and their paths no longer appear simple to an observer standing on the rotating surface. The pendulum shows the ground turning beneath a swinging weight. In the atmosphere and oceans, that same motion causes journeys that seem as though they should be straight to curve gradually instead. Imagine an object being pushed along a straight path across a wide, rotating surface. To an observer standing outside the system, the object continues along its natural trajectory. But to someone standing on the rotating surface, the destination keeps shifting while the object is in motion, making its path appear to curve to one side. No invisible hand is pushing the object sideways, yet an observer within the rotating system still sees it deviate from its original direction. Earth creates a similar effect on a vastly larger scale. The ground, atmosphere, and oceans are all rotating eastward, but their speed in kilometers per hour is not the same at every latitude. Near the equator, a location must travel around the widest circle each day, so it moves eastward more quickly. Toward the poles, the circle becomes smaller and the linear speed decreases. This difference creates no problem when the air, water, and ground remain within the same region. Everything locally already shares nearly the same rotational velocity, allowing a calm day to remain completely peaceful. The situation changes only when an air mass, ocean current, or other object begins traveling far to the north or south. It enters a new region while continuing to carry the eastward velocity of the place where it began. Consider an air mass leaving a region near the equator and moving northward. At its starting point, Earth carries it eastward faster than the ground at higher latitudes. As the air travels toward the pole, its original velocity does not immediately disappear. It gradually moves ahead of the surface below, making its path appear to curve toward the east. To an observer in the northern hemisphere, this deflection lies to the right of the direction of travel. If the air is moving north, east lies to its right. When an air mass from a higher latitude moves southward, it carries a lower eastward velocity than the ground closer to the equator. The surface beneath it moves ahead, making the air appear to fall behind toward the west, which is also to the right of its southward direction. Whether an object moves north or south, an observer in the northern hemisphere sees its path deflected to the right. In the southern hemisphere, the geometry is reversed, and the motion appears to curve toward the left. This phenomenon is known as the Coriolis effect, a direct consequence of observing motion from the surface of a rotating planet. Explaining the effect through differences in eastward velocity makes it easier to visualize, but there is no need to imagine that the air is being pulled sideways by a mysterious force. From a reference frame that does not rotate with Earth, the object is mainly preserving its inertia and continuing along its trajectory. The curve becomes most apparent when that path is described on a map attached to the rotating surface. It is similar to throwing a ball from the center toward the edge of a rotating platform. An observer standing outside may see the ball travel along an almost straight path while the platform turns beneath it. Someone standing on the platform sees the landing point shift away from the original line of aim. Both observers are watching the same motion, but their different frames of reference produce different descriptions of the trajectory. On Earth, the deflection over the distance of a few footsteps is far too small for the body to notice. A ball thrown across a field does not suddenly turn sideways because of the Coriolis effect. Air moving through a room does not bend into an obvious circle simply because the planet is rotating. The effect needs sufficient time and distance to accumulate into a meaningful deviation. When an air mass travels hundreds or thousands of kilometers, the tiny changes occurring each minute begin to add together. A path initially directed straight from high pressure toward low pressure gradually curves. The longer the journey continues, the more time Earth's rotation has to make the trajectory differ from the straight line that someone on the ground might intuitively expect. The Coriolis effect is not equally strong across the entire planet. It is very weak near the equator and becomes more pronounced toward the poles. This pattern helps explain why many large weather systems develop clearly organized rotation at middle and high latitudes, while close to the equator, swirling motion is more difficult to organize in the same way. One notable consequence is that tropical cyclones rarely form directly over the equator. The ocean there may be very warm and moisture may be abundant, but the Coriolis effect is too weak to help a small atmospheric disturbance develop into an organized rotating system. Most tropical storms begin at least several degrees away from the equator, where the influence of Earth's rotation is strong enough to help sustain the circulation. Even so, the Coriolis effect does not create storms by itself. A cold ocean will not produce a tropical cyclone simply because Earth is rotating. The system also requires sufficiently warm surface water to provide energy, moist air, a suitable atmospheric structure, and wind conditions that do not disrupt the developing core. Rotation only helps organize the direction of airflow after other conditions have already set the atmosphere in motion. When a region of low pressure forms, the surrounding air tends to move toward the area of lower pressure. If Earth did not rotate, the air could flow more directly toward the center. On a rotating planet, the Coriolis effect bends the airflow sideways, preventing it from moving straight inward and causing it to begin circling the low-pressure region. In the northern hemisphere, the deflection to the right causes air entering a low-pressure system to develop counterclockwise circulation. In the southern hemisphere, the deflection to the left produces rotation in the opposite direction. This is why tropical cyclones usually spin counterclockwise north of the equator and clockwise to the south. Satellite images of a large storm make this motion clearly visible. Bands of clouds do not move straight toward the eye of the storm. Instead, they curl into long, curved arms. Each part of the air is being drawn toward the center by the pressure difference, while the Coriolis effect continually bends its path sideways. Together, these influences create a spiral structure that can extend across an enormous region of ocean. Near the surface, friction slows the air and alters the balance between the pressure force and the Coriolis effect. As a result, winds may spiral gradually inward toward the center of a low-pressure system rather than simply circling around it. Higher in the atmosphere, where friction is weaker, airflow tends to follow paths more nearly parallel to the pressure lines. The three-dimensional structure of a storm is therefore far more complex than a flat vortex drawn on a map. Around a high-pressure region, air tends to move outward from the center. Earth's rotation bends these currents in the opposite pattern, producing clockwise circulation in the northern hemisphere and counterclockwise circulation in the southern hemisphere. These systems help transport heat, moisture, and clouds across very great distances. The Coriolis effect also helps organize the planet's global wind belts. Air strongly heated by the sun near the equator rises and then moves toward higher latitudes. During this journey, it is deflected eastward. Other air currents returning closer to the surface are bent in their own directions, creating belts of easterly and westerly winds, rather than a simple system blowing directly between the poles and the equator. At middle latitudes, many weather systems commonly travel from west to east, partly because they lie within regions dominated by prevailing westerly winds. High above, jet streams meander around the planet, guiding many low-pressure systems, high-pressure regions, and outbreaks of cold air. Their paths are not completely fixed, but the Coriolis effect is one of the factors that helps maintain the overall pattern of circulation. A similar influence also appears in the oceans. Wind pulls across the surface, setting the upper layers of water in motion. If wind were the only force involved, the water might travel in nearly the same direction as the air. But because Earth rotates, the movement of the water is deflected sideways and transferred into deeper layers in a complex pattern. Across the scale of an entire ocean basin, wind, the Coriolis effect, and continental boundaries help create enormous ocean gyres. In the northern hemisphere, many of these large circulations rotate clockwise, while in the southern hemisphere, they usually turn in the opposite direction. These currents carry heat from warmer regions toward colder ones and help shape climates far from where the water first began its journey. Seawater does not move because of the Coriolis effect alone. Wind supplies part of the driving force. Differences in temperature and salinity produce deeper currents, and continental coastlines and seafloor topography force the water to change direction. Earth's rotation enters the system as a factor that bends long journeys and helps organize the flow into structures spanning the planet. In some places, this influence can be seen when water gathers on one side or moves away from a coastline. When wind blows along the shore, the Coriolis effect can push the surface layer away from land. Cold, nutrient-rich water then rises from below to replace it, creating regions of upwelling that are extremely important for marine life and fisheries. Elsewhere, surface water may be pushed together, forcing part of the flow downward into deeper layers. These vertical movements are not as easy to see as waves on the surface, but they help exchange oxygen, heat, and nutrients between different depths. An effect that begins with planetary rotation can therefore influence entire ocean ecosystems indirectly. Aviation must also account for motion across a rotating planet, but the Coriolis effect does not suddenly push an airplane off course in a way passengers can feel. Navigation systems, wind forecasts, and onboard computers continually correct the aircraft's path using its position, velocity, and atmospheric conditions. On most commercial flights, the direct influence of wind and the curved route across a spherical planet are more noticeable to passengers, while rotational effects are handled within the navigation models. For movements that continue over long distances and require high precision, the Coriolis effect cannot be ignored. The paths of weather balloons, rocket trajectories, meteorological measurements, and certain forms of long-range motion must all be calculated within Earth's rotating frame of reference. A deviation that is tiny during each second can accumulate into a significant distance over a long journey. This does not mean that every object is strongly deflected. Scale determines how important the effect becomes. A falling leaf, a stone thrown by hand, or water flowing through a basin is influenced by forces and disturbances far greater than the Coriolis effect. Only when distance, duration, or required precision increases does the trace of Earth's rotation begin to rise above the background noise. This is why stories about swirling water and sinks are often misunderstood. People sometimes claim that water in the northern hemisphere always drains in one direction, while in the southern hemisphere it must rotate the opposite way. On the small scale of an ordinary sink or toilet, the Coriolis effect is far too weak to determine the outcome reliably. The shape of the container, the position of the drain, the slope of the bottom, and any remaining motion in the water have much greater influence. A slight stir, an uneven stream of water, or a surface that is not perfectly level can be enough to determine the direction of rotation. Two sinks placed beside each other in the same room can easily drain in opposite directions. In carefully controlled experiments, researchers can make the Coriolis influence appear even inside a tank of water. However, the water must be left undisturbed for a long time. The container must be symmetrical, and tiny disturbances must be reduced as much as possible. This shows that the effect is real, while also revealing how weak it is on the scale of everyday life. A storm hundreds of kilometers wide and lasting for several days gives the Coriolis effect enough space and time to shape its rotation. A sink less than a meter across that drains within a few dozen seconds does not. The same law of physics exists in both cases, but its importance is entirely different. The difference in scale also helps explain why people do not feel themselves being pulled sideways while walking. The body travels only short distances, while friction with the ground, muscular movement, and the balance system's continuous adjustments are all far stronger than the Coriolis effect. On a weather map covering an entire continent, however, the deflection becomes impossible to ignore. One simple way to remember the phenomenon is to imagine that an object carries the history of the motion from the place it has just left. Air from near the equator carries a greater eastward velocity as it moves toward the poles. Air from higher latitudes carries a lower eastward velocity as it travels toward the equator. The surface beneath it changes, but the object does not instantly acquire the full velocity of its new location, so its path relative to the ground becomes curved. Although this explanation is useful, the real atmosphere is not divided into separate blocks that slide past one another without interacting. Air masses continually mix, collide, and exchange momentum. Pressure, friction, terrain, and changing temperatures are always involved as well, making actual trajectories more complicated than any idealized example. The Coriolis effect also does not supply energy to winds or storms. It does not naturally make the air move faster. Its primary role is to alter the direction of existing motion rather than create the original energy. The main energy source remains the sun, along with temperature differences and the exchange of heat within the atmosphere and oceans. For this reason, an air current must begin moving before it can be deflected. Pressure differences drive it forward, while the Coriolis effect modifies its path. A current of water must first be set in motion by wind, density differences, or tidal forces before planetary rotation can noticeably influence its direction. This division of roles helps prevent two misunderstandings. Earth's rotation does not directly create every wind, and the Coriolis effect is not the sole cause of every vortex. Rotation is only one part of a much larger system, but on a planetary scale, that part is important enough to reshape the structure of the atmosphere and oceans. The curves seen on weather maps, in the cloud bands of cyclones, and within great ocean gyres are all traces of the same truth. The ground below is not standing still. Every long journey takes place across a rotating surface, so the straight path suggested by intuition no longer remains unchanged as time and distance increase. The Foucault pendulum showed the floor changing direction beneath a swinging weight. The Coriolis effect expands that story across the entire planet. Instead of a wire and a stone floor, the moving objects are now air masses, thousands of kilometers wide, deep ocean currents, and weather systems that may persist for days. But Earth's rotation does not leave traces only across space. It also creates the repeating rhythm humans use to divide life into morning, afternoon, and night. One rotation of Earth becomes one day, but the length of that day is not as simple or constant as the number on a clock might suggest. The sky follows a rhythm of nearly 23 hours and 56 minutes, while everyday clocks use 24 hours. The atmosphere, the oceans, and even the moon also alter Earth's rotational speed by extremely small amounts. After seeing how the planet bends the paths of wind and water, the next question leads us to the largest clock operating around us. How long is a day really? And why does this planetary clock never run with perfect regularity? Every day, the clock returns to the same familiar numbers. 24 hours pass, the hour hand completes 2 full circles, the calendar moves into a new square, and we call it a day. This rhythm repeats so regularly that it is easy to imagine Earth as an enormous machine completing exactly one rotation before beginning again. Yet, when measured with sufficient precision, the planet has never operated in such a simple way. A day is not a fixed gear containing exactly 24 hours. It is the result of many overlapping motions that lengthen or shorten the rotation by mere thousandths of a second. The first complication appears when we try to answer a question that seems remarkably simple. Earth completes one rotation relative to what? If the extremely distant stars are used as a reference, the planet completes one turn in about 23 hours, 56 minutes, and 4 seconds. This interval is known as a sidereal day. After that amount of time, a point on Earth once again faces nearly the same distant region of the sky that it faced before. Human life, however, is not organized according to the positions of distant stars. We wake according to the sun, work while our location is in daylight, and rest when it rotates into darkness. For the sun to return to nearly the same position in the sky, Earth must rotate a little longer than one sidereal day. The reason lies in orbital motion. During those nearly 23 hours and 56 minutes, Earth does not remain fixed in one place while merely rotating on its axis. The planet also moves farther along its path around the Sunday. After completing one full turn relative to the stars, the direction from our location toward the sun is no longer exactly the same as it was at the beginning. Earth must rotate through a small additional angle for the sun to return to nearly the same position in the sky. This extra rotation takes almost 4 minutes. When added to the sidereal day, it gives us the mean solar day of approximately 24 hours, the kind of day used by clocks and daily schedules. The difference of nearly 4 minutes is therefore not a measurement error. It is a trace of the fact that Earth is rotating on its axis while also traveling around the Sunday. This can be pictured as a person walking around a lamp while also turning in place. If the person only needs to face the same direction relative to a distant wall, one full rotation is enough. But during that time, they have moved to a new position along their path around the lamp. To face the light directly once again, they must turn through a little more. Earth performs these same two motions simultaneously, only on a vastly larger scale. This explains why the stars appear about 4 minutes earlier each night when observed at the same clock time. A constellation occupying a certain position tonight will reach that position slightly earlier tomorrow night. The difference is tiny over a single day, but after several weeks, it accumulates enough to change the night sky noticeably with the seasons. Even the 24-hour solar day, however, is not a perfectly fixed value. The word mean is important because the actual sun does not return to the local meridian after exactly the same interval on every day of the year. Earth's orbit is not a perfect circle, and the planet's axis is tilted, causing the length of the apparent solar day to vary slightly. Clocks ignore these variations by using a more stable average day. Even after this averaging, Earth's actual rotation is still not perfectly uniform. A day may be a few milliseconds longer or shorter than the familiar value. The difference is far too small to appear on a household clock, but modern timekeeping systems can detect it clearly. A millisecond is only 1,000th of a second. In that amount of time, light travels nearly 300 kilometers, yet a human being has not even had time to blink. Variations in the length of the day are therefore too small to affect ordinary life directly, but they are important for satellite navigation, space communication, and precise astronomical measurements. Why can such an enormous planet change its rotational rhythm by even these tiny amounts? The answer is that Earth is not a perfectly uniform solid sphere. The atmosphere moves around the planet, ocean currents continually shift, ice accumulates and melts, water moves between land and sea, and material inside Earth follows rhythms of its own. Whenever mass is redistributed, the way the planet rotates can change slightly. The most familiar image is that of a spinning figure skater. When the skater pulls their arms close to the body, they rotate faster. When they extend their arms outward, the rotation slows. The mass has not disappeared. It has simply moved closer to or farther from the axis of rotation, changing the motion. Earth does not literally pull in or extend its arms, but water, ice, and air can move mass closer to or farther from its rotational axis. A large amount of water accumulating in certain regions changes the planet's mass distribution. These changes are extremely small compared with the whole Earth. But when clocks become precise enough, their traces still appear in the length of the day. The atmosphere also exchanges angular momentum with the solid ground below. When major wind belts strengthen or weaken, the amount of motion stored in the air changes. If the atmosphere gains a little rotational momentum, the solid part of the planet may slow by an extremely small amount. When the winds change in the opposite way, the solid Earth may rotate slightly faster. The oceans carry out a similar exchange. Ocean currents, tides, and vast masses of moving water do more than transport heat. They also carry momentum. When the water changes speed or distribution, the rest of the planet must respond so that the total motion of the entire system remains conserved. Even the seasons leave small traces. Winds change throughout the year, snow and ice accumulate in one hemisphere and later melt, and the amount of water stored on the continents rises and falls. No single process is strong enough to lengthen a day by several seconds, but together they cause the planetary clock to fluctuate around its average value. Deep beneath the surface, the story continues. Earth's mantle flows extremely slowly over geological time, while the liquid core moves beneath the solid mantle. Interactions among these internal regions can have a small influence on the rotation observed at the surface. From a distance, the planet may appear to be one unified object, but inside it are many layers moving and affecting one another. Large earthquakes can also redistribute some of the planet's mass in a very short time. When part of Earth's crust shifts, the rotational moment can change by an extremely small amount, causing the length of the day to increase or decrease ever so slightly. These changes are far below anything a person could feel, but they show that even a geological event lasting only a few minutes can leave a trace on the planet's global rhythm. If Earth were the only clock available to humanity, these variations might not create a problem. We could simply call every complete rotation one day, whether it was slightly longer or shorter than the one before. Modern science, however, uses another kind of clock that is far more stable. An atomic clock does not wait for the sun to return to the horizon. It relies on the transition frequency of atoms, a process that can be measured with a regularity far greater than the rotation of the planet. This allows humans to create seconds that remain nearly identical from one day to the next, without depending directly on winds, oceans, or activity deep inside Earth. When these two clocks are placed side by side, the difference begins to emerge. The atomic clock maintains an extraordinarily stable rhythm, while Earth sometimes runs slightly faster or slower. One is a standard of time built by humans from the behavior of atoms. The other is a natural planet influenced by its atmosphere, oceans, ice, groundwater, core, and the moon. For this reason, scientists must continually monitor Earth's orientation relative to extremely distant objects. Radio telescopes, satellites, and other observing systems help determine how quickly the planet is rotating, where its axis is pointing, and how much longer or shorter the actual day is than the average. This information is not used only for research. Navigation systems need to know Earth's exact orientation so they can translate coordinates in space into positions on the surface. A tiny error in time or rotational angle can become a significant positional error when applied across great distances. Space missions depend on the same data. To point an antenna toward a distant spacecraft, engineers must know Earth's position and orientation at every moment. When a ground station sends a signal, the planet continues rotating beneath the transmission path. Even a small error can cause the beam to miss its target. In everyday life, people want noon on the clock to remain close to the time when the sun is highest in the sky. At the same time, science and technology require seconds of consistent length. These two needs are not exactly the same because Earth does not rotate as evenly as an atomic clock. Maintaining the modern time system therefore requires continuous comparison between atomic time and the planet's actual motion. But variations of a few milliseconds are only the short-term story. Across millions of years, another trend emerges. Earth is gradually rotating more slowly. The most important cause is its tidal interaction with the moon. The moon's gravity pulls on the oceans, helping create two tidal bulges on Earth. Because the planet rotates faster than the moon moves along its orbit, these bulges do not remain exactly aligned with the line connecting the two bodies. Instead, they are carried slightly ahead of it. This displaced water exerts a gravitational pull back on the moon. It draws our natural satellite forward along its orbit, transferring a small amount of Earth's rotational energy and angular momentum to the moon. As a result, the moon's orbit slowly expands while Earth's rotation becomes ever so slightly slower. On average, the length of the day increases by about 2.3 milliseconds per century. This does not mean that every century gains exactly the same amount, because many short-term processes can conceal or temporarily alter the trend. Over long timescales, however, tidal effects continue to make the day gradually longer. 2.3 milliseconds in 100 years sounds almost meaningless. An entire human lifetime can pass without anyone feeling the day grow longer. Yet when this tiny change accumulates across hundreds of millions of years, it becomes substantial. In the distant past, Earth rotated faster, and each day was shorter than it is now. Tidal sediment layers and certain fossil growth structures can preserve the rhythms of ancient days, months, and years. They are like natural calendars written into stone, allowing scientists to infer that an ancient year once contained more days. The length of the year had not changed dramatically, but because each day was shorter, Earth had to complete more rotations during one orbit around the Sunday. Earth's gradual slowing does not mean the planet will stop rotating anytime soon. The process is extraordinarily slow and is influenced by many other factors. On the scale of human life, the more important lesson is that a day has never been an entirely isolated unit, separate from the rest of the Earth-Moon system. The atmosphere can make a day longer or shorter by a few thousandths of a second. The oceans transfer momentum between different regions. Ice and water alter the distribution of mass. Earth's core exchanges motion with the mantle. Farther away, the moon quietly takes away a minute portion of rotational energy during every tidal cycle. The planetary clock, therefore, does not operate with a single gear. It resembles a vast system whose many parts continually exchange energy and momentum. The clock face humans observe is the alternation of dawn and sunset, but the inner mechanism extends from high-altitude winds to matter moving deep beneath our feet. Whenever the clock completes another day, Earth does not return to exactly the same state. The planet has moved farther along its orbit around the Sunday. The moon has shifted to a new position. Winds have carried momentum from one region to another. Water has changed its distribution, and currents of material within the planet have continued to move. Even the sky on the following night is not exactly the same as it was before. The stars reach their previous positions a little earlier. The moon changes phase or location, and the angle between Earth and the sun has shifted. We call it the repetition of another day, but in space, no cycle returns precisely to its starting point. What is remarkable is that all this irregularity still creates a rhythm stable enough for life to depend upon. The human body builds its sleep-wake cycle around light and darkness. Plants adjust their activity to the day. Animals migrate, hunt, and reproduce according to rhythms connected to the planet's rotation. An atomic clock may be more regular than Earth, but it does not create dawn. It does not change the direction of a tree's shadow, carry a continent into daylight, or awaken an ecosystem after the night. Earth is an imperfect clock, yet its rotation has created the fundamental rhythm behind nearly every activity on the surface. From the quiet room at the beginning of our story, we have traveled a long way. The sun appears to move because the observer is rotating. The speed beneath every foot may exceed that of an ordinary vehicle, yet the body does not sense it because the motion is so steady and is shared by the surrounding environment. Gravity holds people, oceans, and the atmosphere to the planet, while pendulums, star trails, and the curved paths of winds have made the invisible rotation observable. Now the clock reveals another layer of the story. Earth does not rotate according to a perfectly fixed rhythm. It continually responds to the movement of air, water, ice, matter deep within the planet, and the gravitational pull of the moon. A day appears simple only when it is written as the number 24 hours. In reality, every day is a temporary result of the entire planet. As the clock approaches midnight, Earth does not complete a perfect circle and return to where it began. It simply continues moving, carrying the oceans, the sky, and every living thing into a new part of its orbit, while the planetary clock quietly begins another day that has never existed before. During the time you have been listening to this story, Earth has never stopped. The planet has continued rotating on its axis and moving along its orbit around the Sun, while the Sun and the entire planetary system travel through the Milky Way. At no point along this journey has the room, the bed, or the listener's body ever truly been motionless in space. And yet, none of these movements creates the sensation of rushing forward. The body remains steady on the mattress. Breathing continues in its familiar rhythm, and the air inside the room does not sweep across the skin like a storm. This contrast between immense velocity and a feeling of peace has guided the entire story. How can a rotating planet make those living upon it believe they are completely still? The answer does not lie in a single force or one isolated phenomenon. It emerges from the way everything close to us participates in the same shared motion. Our bodies, the ground, the oceans, and most of the atmosphere do not exist as separate objects struggling to cling to a planet racing beneath them. They already carry Earth's rotational velocity and continue to preserve that motion from one moment to the next. This is why a cup does not slide off a table simply because the room is rotating. When someone jumps, their body does not instantly lose its existing velocity, nor does the ground leave them hundreds of meters behind. The air around them continues moving with the planet, while gravity keeps everything close to the surface instead of allowing it to drift away into space. Gravity does something even more important. It creates the direction of down at every location on Earth. No one truly lives on the underside of the planet, because down is not a fixed direction in the universe. For each person, down points toward Earth's center, while the ground provides the supporting force that prevents the body from continuing to fall under gravity. Rotation modifies this condition only slightly. It contributes to Earth's gentle bulge at the equator and makes effective weight there a little lower. But it comes nowhere close to throwing the oceans or people away from the surface. Life does not exist within a fragile struggle between gravity and rotation. Gravity remains overwhelmingly dominant, holding the entire familiar world to the planet. The atmosphere is not motionless in space, while Earth rotates through it. Gravity keeps the air around the planet, and for a very long time, the atmosphere has shared most of the rotational motion carried by the land and oceans. The wind we feel is only the movement of air relative to the surface, not the shared velocity with which both the atmosphere and Earth are traveling through space. The origin of wind begins instead with imbalance. Sunlight heats the land, water, and different regions of the planet by unequal amounts, creating differences in temperature and pressure. Air moves in response to those imbalances, while Earth's rotation gradually curves the paths of currents traveling over long distances. The same principle appears in cloud bands spiraling around storms, in great ocean gyres, and in air currents crossing vast regions. The Coriolis effect does not create wind, storms, or ocean currents on its own, but it prevents the paths of existing motion from remaining perfectly straight on a map attached to the rotating ground. On a small scale, this influence is too weak to determine the direction in which water drains from an ordinary sink. Across an ocean or within a weather system lasting for several days, however, the small effect accumulates long enough to become an important part of the pattern. Earth does not need to push the air strongly sideways. The surface only needs to keep rotating while air and water move through regions carrying different velocities. Most of this cannot be seen in a single moment. Earth's rotation is concealed by the stability of shared motion, so it leaves only gradual signs. Shadows change direction across the ground. Stars stretch into glowing arcs during long exposures, and a pendulum continues to swing while the floor slowly changes orientation beneath it. These signs do not cause the room to shake or make the horizon tilt. They require time to accumulate because the planet's rotation is far steadier than the kinds of changes the human senses are normally designed to detect. The inner ear readily notices a sudden turn, but remains almost silent during a rotation that takes an entire day. Even the time humans use to describe this rotation is not simple. Relative to the distant stars, Earth completes one turn before the familiar 24-hour mark. The planet must rotate a little farther because while turning on its axis, it has also moved forward along its orbit around the Sunday. That additional interval creates the mean solar day used by the clocks of everyday life. The word mean, however, reminds us that a day is not a unit permanently carved into the planet. Winds can exchange angular momentum with the ground, water shifts between oceans and continents, ice changes location, and matter inside Earth continues to move. These processes make the rotation speed up or slow down by amounts so small that only precise measurements can reveal them. The moon extends the story across much longer spans of time. Tidal interactions gradually transfer a portion of Earth's rotational energy into the moon's orbit, causing the length of the day to increase very slowly. The change is far too small to feel within a human lifetime, yet it shows that this natural clock has never been completely separate from the celestial bodies around it. Atomic clocks can produce seconds that are more uniform than Earth's rotation. Even so, it is the planet that creates the alternation of light and darkness, carrying each region into sunlight and then back into night. An artificial clock measures time with extraordinary precision, while the planetary clock creates the rhythm of life that this measurement is used to describe. A day, then, is not merely the interval between two moments when the hands of a clock return to the same position. During that time, Earth has moved farther along its orbit, winds and water have redistributed momentum, the moon has traveled to a new location, and the night sky has changed slightly from the day before. Daily life feels repetitive, but the entire system never returns to exactly the same state. Now let your view move back from orbit, the atmosphere, and the ocean currents to the room where this story began. The table still stands beside the wall, the glass of water has not slipped from the edge, and the floor still feels solid beneath the body. Nothing in the room reveals that it has just been carried across an immense distance around Earth's axis. This stillness is not entirely an illusion. The room truly is almost motionless relative to the person lying inside it, just as the glass is motionless relative to the table and the air moves only slowly relative to the walls. What must change is only the meaning of the word still. It does not describe the absence of all motion, but the fact that nearby objects share nearly the same velocity. People often imagine that motion must reveal itself through noise, powerful winds, or scenery rushing past. Earth shows us another possibility. When motion is steady enough and the entire environment participates in it, tremendous velocity can exist without creating any sense of urgency. Perhaps the strangest thing, then, is not how rapidly Earth is rotating. Stranger still is that a planet can carry mountains, oceans, the sky, and billions of living beings within an immense motion, while allowing each person to feel as though they are lying perfectly still. Inside the quiet room, breathing remains steady, the glass of water stays on the table, and the darkness outside continues to change slowly. Earth keeps turning beneath all these familiar things, not like a machine dragging us along, but as the shared motion that has carried and supported all life from the very beginning.